Imagine standing on the edge of the observable universe, looking out into an endless sea of galaxies, stars, and unknown worlds. Beyond the boundaries of our solar system, past the edges of our galaxy, lies a vast, interconnected web of mysteries, from invisible forces shaping cosmic structures to realms of space-time that bend and twist under gravity's influence. In this video, we'll dive deep into the wonders of the cosmos, exploring the powerful forces, strange phenomena, and mind-bending theories that shape our understanding of reality. From the depths of black holes to the vast expanses of intergalactic space, we'll uncover the incredible science behind what we see and what we can only imagine out there in the great expanse. Primordial gravitational waves, echoes from the Big Bang, continued. Primordial gravitational waves are thought to have been generated during the era of cosmic inflation, a period of rapid exponential expansion that occurred just fractions of a second after the Big Bang. During inflation, tiny quantum fluctuations in space-time were stretched to cosmic scales, creating ripples that we believe should still be present today as gravitational waves. Unlike gravitational waves generated by modern astrophysical events, these primordial waves would be incredibly faint, leaving only a subtle imprint on the cosmic microwave background, CMB. Detecting primordial gravitational waves is one of the primary goals of modern cosmology. These waves could provide a direct window into the universe's earliest moments, revealing details about the inflationary process, the energy scales involved, and potentially the fundamental forces that shape the universe's structure. In particular, the B-mode polarization pattern in the CMB caused by these ancient gravitational waves could serve as a signature of inflation. If detected, B-mode polarization would not only confirm inflation but also offer insights into the energy scales that governed the early universe. Experiments like the BICEP, background imaging of cosmic extragalactic polarization, and the South Pole Telescope have been dedicated to searching for these B-mode patterns in the CMB. While there have been hints of detection, the signal is incredibly faint, requiring precise measurements and careful differentiation from foreground effects, such as dust in the Milky Way. Future missions, including the proposed LIGHT-by-RD, Light Satellite, for the study of B-mode polarization and inflation from cosmic background radiation detection, and the CMES-4 project, aim to improve sensitivity, potentially allowing us to detect primordial gravitational waves directly. The study of primordial gravitational waves pushes the boundaries of our understanding of the cosmos. These waves carry the fingerprint of the universe's birth, offering clues about the forces and processes that shaped space-time itself. Detecting them would be one of the most significant discoveries in physics, linking cosmology with quantum mechanics and the quest to unify the fundamental forces in a theory of everything. Fast radio bursts, mysterious signals from deep space. Fast radio bursts, FRBs, are brief but extremely powerful bursts of radio waves that last only milliseconds, yet they emit as much energy in a fraction of a second as the sun does in a day. Discovered in 2007, FRBs remain one of the most mysterious phenomena in astronomy. Although hundreds of FRBs have been detected since their discovery, their origins are still unknown, and only a small fraction of them have been observed to repeat. FRBs are thought to originate from distant galaxies, with some located billions of light-years away. Their exact cause, however, remains elusive. Possible explanations range from highly magnetized neutron stars, known as magnetars, to collisions between neutron stars, black holes, or even exotic phenomena like cosmic strings. The short duration and unpredictable nature of FRBs make them challenging to study, but recent observations have begun to reveal patterns in some repeating FRBs, offering clues about their origin. One of the breakthroughs in studying FRBs came with the discovery of localized bursts, where the precise location of an FRB was pinpointed to a specific galaxy. This allowed astronomers to measure the distance to the FRB and study its surrounding environment. In some cases, FRBs have been associated with regions of intense star formation, hinting that they may be linked to young, highly magnetic neutron stars or other high-energy environments. The detection of FRBs has implications for cosmology as well. Since radio waves from FRBs travel through intergalactic space, they interact with electrons and other particles, providing a way to measure the density and composition of the material between galaxies. By analyzing the dispersion of FRBs, scientists can map the distribution of matter in the universe, including the elusive missing baryons ordinary matter that has not yet been detected in visible form. Fast radio bursts remind us of the mysteries that still lie beyond our understanding. They offer a new window into high-energy processes in the universe and the extreme environments that produce such powerful emissions. As we continue to observe and analyze FRBs, each detection brings us closer to unraveling the nature of these enigmatic signals from deep space. Planck time and the limits of physical reality. Planck time is the smallest meaningful unit of time, a concept that arises from combining the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant. This tiny interval, approximately 1043 seconds, represents the quantum limit of time, beyond which our current understanding of physics breaks down. Planck time marks the scale at which both quantum mechanics and general relativity influence the fabric of space-time, suggesting that a new theory of quantum gravity may be required to describe reality at such minuscule scales. Planck time is significant because it sets the boundary for our knowledge of the universe's earliest moments. During the first Planck second after the Big Bang, the universe was unimaginably hot and dense, with energy levels so extreme that space and time, as we know them, may not have existed in their current form. It is within this interval that physicists believe quantum fluctuations in space-time could have laid the groundwork for the structure of the universe, potentially sparking the process of cosmic inflation. The concept of Planck time challenges our understanding of causality and time itself. At scales smaller than the Planck time, traditional notions of cause and effect may not apply, as quantum uncertainty dominates. This limitation means that current theories cannot describe what happened during the Planck era, leaving a gap in our understanding of the universe's birth. Bridging this gap requires a theory of quantum gravity that could unify general relativity with quantum mechanics. The quest to understand Planck time and the quantum nature of space-time has led physicists to explore speculative theories, such as string theory and loop quantum gravity. These theories suggest that space-time itself may be quantized, composed of discrete units or loops at the Planck scale. If true, this quantization would revolutionize our understanding of reality, revealing a fundamental granularity to space and time that is invisible at larger scales. Planck time represents the frontier of physics, where our current theories reach their limits and new, unknown physics may await. It reminds us that the universe operates on scales far beyond human experience, challenging us to rethink the nature of time, space, and the fundamental structure of reality. The Higgs field, giving Massachusetts to the universe. The Higgs field is a fundamental field that permeates the entire universe, providing particles with mass through their interaction with the Higgs boson, a particle first discovered in 2012 at the Large Hadron Collider, LHC. The existence of the Higgs field was first proposed in the 1960s to explain why particles, such as protons and electrons, have mass rather than traveling at the speed of light like photons. Without the Higgs field, particles would remain massless, and matter as we know it could not form. The Higgs boson is often called the God particle due to its fundamental role in the structure of the universe. When particles move through the Higgs field, they acquire mass, similar to how objects moving through a viscous fluid experience resistance. The more a particle interacts with the Higgs field, the greater its mass. Particles that do not interact with the Higgs field, like photons, remain massless and travel at the speed of light. The discovery of the Higgs boson confirmed the last missing piece of the standard model of particle physics, which describes the fundamental particles and forces, except for gravity, that govern the universe. However, the Higgs field also raises new questions. For example, the mass of the Higgs boson itself does not seem to match theoretical predictions, leading scientists to explore fine-tuning problems that suggest new physics beyond the standard model. The Higgs field is also linked to the early universe. During cosmic inflation, the Higgs field may have played a role in shaping the expansion of space. Some theories propose that fluctuations in the Higgs field could have contributed to the formation of large-scale structures, potentially influencing the distribution of galaxies in the cosmic web. The Higgs field is a testament to the power of human curiosity and scientific discovery. Its existence was hypothesized decades before it was observed, and its confirmation opened a new chapter in our understanding of the universe's fundamental nature. The Higgs field reminds us that fields, rather than particles alone, play a vital role in shaping the cosmos, influencing everything from the mass of atoms to the evolution of galaxies. The Oort cloud, a distant reservoir of comets. The Oort cloud is a theoretical shell of icy objects that surrounds the solar system at a vast distance, far beyond the Kuiper belt and the orbit of Pluto. Extending from about 2,000 to 100,000 astronomical units from the Sun, the Oort cloud is thought to be the source of long-period comets, those with orbits that take thousands or even millions of years to complete. Although it has not been directly observed, the Oort cloud remains a key component of solar system models, explaining the origin of comets that periodically visit the inner solar system. The objects in the Oort cloud are believed to be remnants from the early solar system, composed mainly of ice and rock. These distant bodies were likely scattered to the outer reaches of the solar system by gravitational interactions with the giant planets, especially Jupiter and Saturn. As a result, the Oort cloud represents a fossil record of the solar system's formation, preserving materials from its earliest days. The Oort cloud is divided into two regions, the inner Oort cloud, which forms a thick disk, and the outer Oort cloud, a spherical shell that surrounds the solar system. Occasionally, objects from the Oort cloud are perturbed by passing stars, galactic tides, or other gravitational influences, sending them into the inner solar system as long-period comets. These comets offer a unique opportunity to study primordial material from the outer reaches of the solar system. The existence of the Oort cloud also raises questions about the solar system's interactions with other stars and the galaxy itself. Some scientists propose that the Oort cloud may contain objects captured from other star systems, providing clues about the Sun's early environment in a stellar nursery. Studying these distant objects could reveal more about the Sun's formation and the dynamics of the Milky Way's stellar neighborhoods. The Oort cloud represents the boundary of the Sun's gravitational influence and serves as a reminder of the vastness of the solar system. Although it remains beyond the reach of current technology, the Oort cloud is a testament to the solar system's complex history and the enduring mysteries that lie at the edges of our cosmic neighborhood. The quantum vacuum, energy in emptiness. The concept of the quantum vacuum challenges our traditional idea of empty space. In classical physics, a vacuum is a space entirely devoid of matter, with no particles or energy. However, in quantum mechanics, even the emptiest space is far from empty. The quantum vacuum is a seething field of energy where virtual particles continually pop in and out of existence due to fluctuations in energy. This vacuum energy, also known as zero-point energy, has profound implications for both physics and cosmology. Virtual particles in the quantum vacuum appear and disappear on incredibly short timescales, creating fleeting disturbances that give rise to measurable effects. One of the most famous consequences of this phenomenon is the Casimir effect, where two closely spaced metal plates in a vacuum experience an attractive force due to changes in the quantum vacuum between them. This effect demonstrates that the vacuum is not truly empty but filled with fluctuating fields and particles that exert forces on matter. The quantum vacuum also plays a role in the origin of the universe itself. Some theories propose that the universe could have emerged as a quantum fluctuation within the vacuum, giving rise to the Big Bang and cosmic inflation. In this view, the quantum vacuum is a reservoir of potential energy, from which entire universes could theoretically bubble up and expand. This idea aligns with some interpretations of the multiverse theory, where countless universes arise from quantum fluctuations in a broader meta-vacuum. In cosmology, the energy of the quantum vacuum is also associated with dark energy, the mysterious force driving the universe's accelerated expansion. The cosmological constant, which represents the energy density of empty space, might be related to the energy of the quantum vacuum. However, theoretical calculations of this vacuum energy differ significantly from observed values, leading to the cosmological constant problem, one of the biggest unsolved puzzles in physics. The quantum vacuum invites us to reconsider the nature of emptiness and the boundaries of physical reality. It reveals that nothingness is not truly empty but a dynamic space filled with potential and energy. The quantum vacuum is a reminder that even the most fundamental aspects of existence, space, time and matter, are interconnected, and that reality itself may be more complex and layered than we can currently imagine. Cosmic voids, the empty spaces between galaxies. Cosmic voids are vast regions in the universe that contain very few galaxies, stars, or matter. These empty spaces, which can span hundreds of millions of light years, are surrounded by the denser regions of the cosmic web, where galaxies and clusters form along filaments of dark matter. Voids make up a significant portion of the universe. Yet they are some of the least understood structures in cosmology, challenging our understanding of how matter is distributed on the largest scales. Cosmic voids form naturally as part of the large-scale structure of the universe. In the early universe, tiny density fluctuations led to the gradual clumping of matter, creating a network of filaments, clusters, and voids. Over billions of years, gravitational interactions drew matter toward dense regions, leaving behind the sparse regions we observe today as voids. These voids are not completely empty, as they contain dark matter, gas, and occasional small galaxies, but their density is much lower than surrounding regions. Studying cosmic voids provides unique insights into the properties of dark energy and the universe's expansion. Since voids have low gravitational influence, they expand faster than denser regions, making them ideal laboratories for measuring the effects of dark energy. Observing how light from distant galaxies travels through voids also allows astronomers to study the distribution of dark matter and test models of cosmic structure formation. Voids also affect the galaxies that reside within them. Galaxies in voids tend to be isolated and exhibit slower rates of star formation compared to galaxies in clusters. This difference provides clues about how environment influences galaxy evolution, with void galaxies representing a more pristine population unaffected by the dense gravitational fields and interactions found in clusters. Cosmic voids reveal the scale and complexity of the universe's structure, where galaxies are connected by vast, empty spaces. These voids challenge our perception of the universe as a continuous, uniform space, showing instead that the cosmos is a patchwork of dense and sparse regions shaped by gravity and dark matter. The study of voids reminds us that even in emptiness, there is structure, pattern, and meaning, adding to the mystery of the universe's design. The fine structure constant, a fundamental number of the universe. The fine structure constant, often denoted by the Greek letter alpha, A, is a dimensionless constant that describes the strength of the electromagnetic force between charged particles, such as electrons and protons. This constant plays a fundamental role in determining the behavior of atoms, molecules, and even the structure of stars. The value of alpha, approximately 1/137th, is one of the universe's magic numbers, as its exact value affects nearly every aspect of atomic and molecular physics. The significance of the fine structure constant goes beyond its role in electromagnetic interactions. Alpha's value influences the stability of atoms, the wavelengths of light emitted by atoms, and even the processes that govern stellar fusion. If alpha were slightly different, atoms as we know them might not exist, and life itself could be impossible. This sensitivity has led some scientists to wonder why alpha has precisely this value, and whether it might vary in different regions or epochs of the universe. The possibility that the fine structure constant could vary over time or space remains an open question. Observations of distant quasars and other cosmic phenomena have hinted at slight variations in alpha, but these findings are still under debate. If confirmed, a changing fine structure constant would imply that the fundamental forces of nature are not as constant as we once believed, opening new avenues of inquiry into the nature of physical laws and the potential for other universes with different constants. The fine structure constant's mysterious origin has led to speculation about its role in a broader framework, such as the multiverse or theories of higher dimensions. Some scientists propose that alpha's value might be a product of underlying physics in a higher dimensional space, or that it could vary across a landscape of possible universes in the multiverse. These ideas remain speculative, but they highlight the fundamental role of constants like alpha in shaping the universe's properties. The fine structure constant serves as a reminder of the deep interconnections within physics. It shows that even seemingly abstract numbers can have profound consequences for the structure of reality, influencing everything from the glow of stars to the complexity of life. The fine structure constant is one of the universe's hidden keys, a constant that defines the rules by which matter and energy interact. Galactic cannibalism, the fate of merging galaxies. Galactic cannibalism is a process in which larger galaxies consume smaller ones through gravitational interactions. Over billions of years, galaxies can collide, merge, and absorb one another, with the larger galaxy often absorbing stars, gas, and dark matter from its smaller companion. This process reshapes galaxies, fueling star formation and altering their structure and dynamics. Galactic cannibalism is an essential aspect of cosmic evolution, contributing to the formation of massive galaxies and galaxy clusters. When galaxies collide, their stars rarely collide directly due to the vast distances between them. However, the gas within galaxies does interact, creating shock waves that compress the gas and trigger bursts of star formation. These starburst events can produce thousands of new stars, illuminating the merging galaxies and creating beautiful displays of color and light. Over time, gravitational forces cause the galaxy's structures to warp and stretch, ultimately resulting in a single, larger galaxy. The Milky Way itself has engaged in galactic cannibalism, consuming smaller galaxies over its history. Evidence of these past interactions is visible in the form of stellar streams, trails of stars left behind by absorbed dwarf galaxies. The Sagittarius dwarf galaxy, for example, is currently being torn apart by the Milky Way's gravity, its stars forming a stream around our galaxy. In billions of years, the Milky Way is also expected to collide with the Andromeda galaxy, leading to the formation of a new, larger galaxy. Galactic cannibalism plays a crucial role in the growth of galaxies and the formation of galaxy clusters. Massive galaxies, such as elliptical galaxies found in the centers of clusters, are often the result of multiple mergers, accumulating stars and dark matter over time. These galaxies become cosmic giants, dominating their surroundings and influencing the structure of galaxy clusters. The study of galactic cannibalism provides insights into the dynamic nature of the cosmos. It shows that galaxies are not isolated entities, but are part of a larger cosmic ecosystem, where gravitational interactions shape their growth and evolution. Galactic cannibalism reminds us that the universe is a place of constant change, where galaxies themselves are transient structures, merging and transforming over billions of years. Boltzmann brains, a bizarre hypothetical thought experiment. The concept of Boltzmann brains arises from a thought experiment in cosmology and statistical mechanics, questioning the nature of consciousness and the likelihood of self-aware observers in the universe. Named after the physicist Ludwig Boltzmann, this idea suggests that given an infinite amount of time, random fluctuations in a universe could produce self-aware entities, disembodied brains that form purely by chance from particles in a state of thermal equilibrium. The Boltzmann brain hypothesis stems from the idea that in a universe dominated by randomness, fluctuations can occasionally create complex structures. In an infinite universe, it is statistically possible that a conscious brain could arise from a random arrangement of particles, complete with memories and perceptions, despite having no prior existence or physical surroundings. Such an entity would be a brief fluctuation, existing momentarily before dissolving back into randomness. The concept of Boltzmann brains raises philosophical and scientific questions about the nature of reality and observation. If Boltzmann brains are statistically more likely than actual human observers in an infinite universe, it could lead to a paradox. How do we know that we ourselves are not Boltzmann brains? This notion challenges assumptions about the continuity of consciousness, the reliability of memories, and the nature of existence itself. Physicists debate the implications of Boltzmann brains in cosmology, especially in the context of models of eternal inflation and the multiverse. Some argue that a universe where Boltzmann brains outnumber ordinary observers would be unstable or incoherent, suggesting that our understanding of cosmology might need refinement. Others contend that the existence of Boltzmann brains, while theoretically possible, does not affect practical observations or the everyday experience of conscious beings. Boltzmann brains remain a speculative and philosophical topic, a thought experiment that pushes the boundaries of physics, consciousness, and probability. While unlikely to affect our daily lives, the concept challenges our understanding of existence, reminding us that the universe may operate in ways that are deeply counterintuitive and beyond human comprehension. Dark matter, the hidden Massachusetts of the universe. Dark matter is a mysterious and invisible substance that makes up approximately 27% of the universe, yet it does not emit, absorb, or reflect light, making it undetectable through direct observation. Its existence was first proposed to explain the gravitational effects observed in galaxies and galaxy clusters, which could not be accounted for by visible matter alone. Although dark matter has never been directly detected, its gravitational influence on ordinary matter is undeniable, shaping the structure of galaxies, clusters, and the cosmic web. One of the strongest pieces of evidence for dark matter comes from the study of galaxy rotation curves. When astronomers measure the speed at which stars orbit the centers of galaxies, they find that outer stars move faster than expected based on the visible mass of the galaxy. This unexpected speed suggests the presence of additional, unseen mass exerting gravitational force on the star's mass that we attribute to dark matter. Dark matter is also essential for understanding the formation of galaxies and large-scale structures in the universe. In the early universe, dark matter acted as a gravitational scaffold around which gas could accumulate, forming stars and galaxies. Without dark matter, galaxies would not have formed in the way they did, and the universe would look vastly different. Dark matter is thought to clump together in halos around galaxies, providing the necessary gravitational pull to hold them together. Scientists have proposed several candidates for dark matter particles, including WIMPs, weakly interacting massive particles, and actions, but none have been definitively detected. Experiments such as the Large Underground Xenon, LOAX detector and the Alpha Magnetic Spectrometer on the International Space Station are among the many efforts to detect dark matter particles directly. Despite its elusiveness, dark matter remains one of the most critical components of the universe, influencing its evolution on both small and cosmic scales. Dark matter challenges our understanding of the universe's fundamental composition, reminding us that the visible world is only a fraction of what exists. It raises questions about the nature of matter, gravity, and the unknown forces that shape the cosmos. The study of dark matter offers a glimpse into the hidden workings of the universe, a reminder that there is still much we do not know about the nature of reality. Dark energy, the force behind the universe's accelerated expansion. Dark energy is an even more mysterious force than dark matter, making up about 68% of the universe. It is believed to be responsible for the accelerated expansion of the universe, a discovery that shocked scientists in the late 1990s. Observations of distant supernovae showed that galaxies were moving away from each other faster than expected, suggesting that a force stronger than gravity was driving this expansion. The exact nature of dark energy remains unknown, but it is often associated with the cosmological constant, a term originally introduced by Einstein in his equations of general relativity. While Einstein initially used the cosmological constant to balance the force of gravity, he later discarded it, calling it his greatest blunder. However, the discovery of dark energy has resurrected this idea, with the cosmological constant now representing the energy density of empty space. Dark energy's effects are visible on the largest scales of the universe. It acts as a repulsive force, counteracting gravity and causing galaxies to drift apart at an ever-increasing rate. Over billions of years, dark energy will continue to drive the expansion, leading to scenarios like the Big Freeze, where galaxies move so far apart that stars burn out and the universe becomes cold and dark. There are various theories about the nature of dark energy. Some suggest it might be a property of space itself, while others propose that it could be the result of a dynamic field, often called quintessence, that changes over time. Understanding dark energy is one of the biggest challenges in modern cosmology, as it could fundamentally alter our understanding of the universe's fate and the forces that govern it. Dark energy is a profound mystery, hinting at forces beyond our comprehension. It challenges our perception of space and time, suggesting that the universe is not a static entity but a dynamic system shaped by forces that stretch the limits of human understanding. The study of dark energy is a journey into the unknown, a quest to uncover the true nature of the cosmos and its ultimate destiny. Antimatter, the universe's mirror image. Antimatter is the counterpart to ordinary matter, with particles that have the same mass but opposite charges. For example, the antimatter counterpart of an electron is the positron, which has a positive charge instead of a negative one. When matter and antimatter meet, they annihilate each other in a burst of energy, a process that releases gamma rays and can be harnessed as a potential energy source. The existence of antimatter was first predicted by physicist Paul Dirac in 1928, and it was later confirmed experimentally with the discovery of the positron. Since then, scientists have produced small amounts of antimatter in particle accelerators, but naturally occurring antimatter is rare. One of the biggest questions in cosmology is why the universe appears to be dominated by matter, as the Big Bang should have produced equal amounts of matter and antimatter. The scarcity of antimatter in the universe leads to what is known as the baryon asymmetry problem. Some theories suggest that certain interactions in the early universe led to a slight imbalance, allowing matter to prevail over antimatter. Discovering the cause of this asymmetry could provide insights into the fundamental laws of physics and the processes that shaped the early universe. Antimatter also has practical applications, particularly in medical imaging. Positron emission tomography (PT) scans use antimatter to detect metabolic activity in the body, allowing doctors to identify tumors and study brain function. While antimatter remains challenging to produce and store, its unique properties make it a valuable tool for science and medicine. Antimatter challenges our understanding of the universe's fundamental symmetry, raising questions about why matter dominates over its mirror image. It offers a glimpse into the hidden balance of forces that shape the cosmos, reminding us that reality has layers of complexity beyond what we observe. Hawking radiation and black hole evaporation. Hawking radiation, a theoretical prediction by physicist Stephen Hawking, suggests that black holes are not entirely black but emit a faint radiation due to quantum effects near their event horizons. This radiation is caused by virtual particle pairs that form near the event horizon. When one particle falls into the black hole and the other escapes, the black hole loses a tiny bit of mass, gradually evaporating over time. This discovery revolutionized our understanding of black holes, showing that they are not static objects but dynamic systems that interact with the quantum vacuum. According to Hawking's theory, black holes have entropy, or disorder, and must obey the laws of thermodynamics. This led to the formulation of black hole thermodynamics, where properties like temperature, entropy, and surface area are connected, transforming black holes from mysterious objects into something that follows predictable rules. Hawking radiation also introduces the black hole information paradox, a major puzzle in theoretical physics. Since information cannot be destroyed according to quantum mechanics, the gradual evaporation of a black hole raises the question of what happens to the information contained within it. This paradox has led to various proposed solutions, including the idea that information might be stored on the event horizon in a holographic way, or that it could escape in some form. Although Hawking radiation is extremely weak for large black holes, making it nearly impossible to detect, micro-black holes, if they exist, would emit detectable levels of radiation before evaporating completely. This idea has sparked interest in experiments and particle accelerators that could create tiny black holes, potentially providing direct evidence of Hawking radiation. Hawking radiation challenges our understanding of space-time, entropy, and the nature of information. It bridges the worlds of quantum mechanics and general relativity, pointing toward a unified theory of physics that could explain both the microscopic and cosmic realms. Hawking's theory reminds us that even the most enigmatic objects in the universe obey fundamental principles, providing a glimpse into the underlying order of reality. The arrow of time. Why does time move forward? The arrow of time is a concept that describes the one-way direction or flow of time, from past to future. This phenomenon is closely related to the second law of thermodynamics, which states that entropy, or disorder, always increases over time. As systems become more disordered, time appears to progress forward, creating an irreversible sequence of events from past to present to future. One of the greatest mysteries in physics is why time has a direction at all. In most physical laws, time is symmetric, meaning that the equations work the same whether time flows forward or backward. However, in our everyday experience, time moves in only one direction. This asymmetry, known as time's arrow, is deeply connected to the concept of entropy and the conditions of the early universe. Cosmologists believe that the low entropy state of the universe after the Big Bang set the conditions for time's arrow. As the universe expanded, entropy increased, leading to the irreversible progression of time. If the universe were to reach a state of maximum entropy, known as heat death, time's arrow would effectively cease, as there would be no further increase in disorder. The arrow of time also has implications for our understanding of causality and memory. Our perception of the past, present, and future is influenced by the direction of time, affecting everything from the evolution of the universe to our experiences of life. The arrow of time raises profound questions about the nature of reality, challenging us to understand why the universe began in a low entropy state, and what, if anything, lies beyond the boundaries of time. The arrow of time is a reminder that our experience of reality is shaped by fundamental forces and conditions beyond our control. It highlights the connections between thermodynamics, cosmology, and the nature of existence, suggesting that time's flow is one of the universe's most fundamental properties. The end of the universe. Possible scenarios for cosmic fate. The ultimate fate of the universe is one of the most profound questions in cosmology, with several potential outcomes based on current scientific understanding. These scenarios depend on factors like the density of matter, the nature of dark energy, and the geometry of the universe. The most widely discussed possibilities are the Big Freeze, the Big Rip, and the Big Crunch. In the Big Freeze, also known as heat death, the universe continues expanding indefinitely. Over time, galaxies drift apart, stars burn out, and black holes slowly evaporate due to Hawking radiation. Eventually, all matter decays, leaving a cold, dark universe filled with only low-energy photons and particles. This scenario leads to a state of maximum entropy, where no organized structures remain, and time's arrow effectively stops. The Big Rip is a more dramatic scenario, where dark energy grows stronger over time, accelerating the expansion of the universe until it tears apart galaxies, stars, and even atoms. In this scenario, the fabric of space-time itself is stretched to the breaking point, resulting in a catastrophic end to all matter. The timeline for a Big Rip depends on the behavior of dark energy, which remains a topic of ongoing research. The Big Crunch is the opposite of the Big Freeze. In this scenario, the expansion of the universe eventually reverses, causing galaxies to collapse back together. This contraction leads to a hot, dense state similar to the conditions of the Big Bang, potentially resulting in a cosmic rebirth through a new Big Bang. While current observations suggest that the universe is expanding and accelerating, the Big Crunch remains a possibility if dark energy changes over time. The study of the universe's fate combines observations of cosmic expansion, dark energy, and the large-scale structure of the cosmos. Each scenario offers a different vision of cosmic evolution, challenging us to consider the ultimate limits of time, space, and existence. The end of the universe is a question that transcends science, inviting us to reflect on the mysteries of creation, change, and the nature of reality itself. Dark matter and the invisible universe. What if most of the universe's mass is something we can't even see? Dark matter remains one of the most elusive components of the cosmos, detectable only through its gravitational effects on visible matter. We'll explore the role dark matter plays in shaping galaxies and holding clusters together, how scientists are searching for direct evidence of it, and the profound impact its discovery could have on our understanding of the universe. The cosmic web, the universe's giant structure. Zoom out from a single galaxy, and you'll see it as a part of a much larger structure, a vast, interconnected cosmic web that stretches across the universe. This network of filaments, voids, and clusters forms the large-scale structure of the cosmos, with galaxies and dark matter creating intricate patterns. Formed over billions of years as matter clumped together due to gravity, the cosmic web is shaped by forces we can't fully see or measure. Yet it reveals the universe's hidden architecture. Scientists studying the cosmic web use massive surveys and simulations to map its structure. The patterns they uncover help reveal the nature of dark matter and even hint at the role of dark energy in the universe's expansion. By observing how galaxies cluster and voids form, researchers gain insights into the universe's origins and evolution, revealing that everything is interconnected in ways beyond our everyday experience. Neutron stars, ultra-dense remnants of supernova explosions. When massive stars reach the end of their lives, they explode in supernovae, leaving behind incredibly dense cores known as neutron stars. Imagine a mass greater than the Sun packed into a sphere only about 20 kilometers in diameter. Neutron stars are so dense that a single teaspoon of their material would weigh billions of tons on Earth. These cosmic remnants exhibit extraordinary properties, such as extreme magnetic fields and rapid rotation. Some neutron stars, known as pulsars, emit beams of electromagnetic radiation from their poles, creating a lighthouse effect as they spin. Others, like magnetars, have magnetic fields trillions of times stronger than Earth's. Studying neutron stars gives us a glimpse into the extreme physics of matter and energy at scales we can't replicate on Earth. Quasars, beacons from the early universe. Quasars are some of the most luminous and energetic objects in the universe, powered by supermassive black holes at the centers of young galaxies. As matter falls into the black hole's accretion disk, it heats up and emits intense radiation, outshining entire galaxies and becoming visible across billions of light years. Quasars serve as cosmic lighthouses, illuminating the distant reaches of the universe and helping scientists study its earliest stages. Observing quasars, astronomers to look back in time, to an era when galaxies were first forming. The light from these quasars has traveled across billions of years, revealing the conditions of the early universe. By analyzing quasar light as it passes through intergalactic gas, scientists map the large-scale structure of the universe and uncover clues about the distribution of matter, the presence of dark matter, and the evolution of cosmic structures. The expanding universe and the discovery of dark energy. In 1998, scientists made a surprising discovery: the universe's expansion is accelerating. Rather than slowing down due to gravitational pull, galaxies are moving away from each other at an increasing rate. This phenomenon is attributed to dark energy, a mysterious force that makes up about 68% of the universe and counteracts gravity. The discovery of dark energy has fundamentally changed our understanding of the universe's fate. Instead of collapsing back in on itself, the cosmos may continue expanding indefinitely, with galaxies drifting further apart until they become isolated in an endless void. This big freeze scenario raises profound questions about the future of the universe and our place within it. Studying dark energy is one of the biggest challenges in cosmology. Scientists use observations of distant supernovae, cosmic background radiation, and large-scale structures to understand its properties, but its true nature remains elusive. Whether dark energy is a property of space itself, a dynamic field, or something entirely unknown, it is reshaping our understanding of the universe's evolution and destiny. Black holes and the mystery of event horizons. Black holes are among the universe's most mysterious objects, with gravitational fields so intense that nothing, not even light, can escape their pull. At the core of a black hole is the event horizon, a boundary beyond which escape is impossible. Once something crosses this threshold, it's lost to the black hole's singularity, where gravity compresses matter to an infinite density. Black holes come in various sizes, from stellar mass black holes formed by collapsing stars to supermassive black holes that anchor galaxies. Scientists have also theorized about primordial black holes that may have formed soon after the Big Bang. The study of black holes has led to incredible insights into the nature of space and time, as well as the limits of our understanding of physics. The concept of Hawking radiation, proposed by Stephen Hawking, adds another layer of mystery to black holes. According to this theory, black holes emit faint radiation due to quantum effects near the event horizon, causing them to slowly lose mass and eventually evaporate. If confirmed, Hawking radiation would link quantum mechanics with general relativity, two of the most fundamental but incompatible theories in physics. The multiverse, beyond our universe. The concept of the multiverse suggests that our universe might be one of countless others, each with its own laws of physics, dimensions, and constants. In this view, the observable universe could be just a single bubble in an endless sea of universes, each forming its own unique reality. The multiverse theory is supported by some interpretations of quantum mechanics, string theory, and cosmic inflation, all of which hint that the cosmos may extend far beyond the boundaries of what we can observe. In some models, different universes are separated by vast distances or alternate dimensions, while others suggest they may exist side by side, only separated by subtle variations in physical laws. One popular theory, the many worlds interpretation of quantum mechanics, proposes that every possible outcome of a quantum event creates a new, parallel universe, leading to a vast branching of realities. This theory, while speculative, has profound implications for our understanding of reality and the nature of choice and chance. If the multiverse exists, it may help explain why our universe's physical constants seem finely tuned to allow life. In a multiverse with countless universes, each with different properties, it's statistically likely that at least one would have conditions suitable for life. While we currently have no direct evidence for the multiverse, researchers are exploring ways to detect its effects, such as subtle imprints on the cosmic microwave background that might indicate interactions with other universes. The multiverse is a mind-bending idea, pushing the limits of what we can imagine. It challenges us to think beyond our observable reality, suggesting that our universe is only one chapter in an infinite cosmic story. The Fermi Paradox: where are all the aliens? Given the vast number of stars and planets in the universe, it seems likely that intelligent life could exist elsewhere. Yet, despite decades of searching, we have no concrete evidence of extraterrestrial civilizations. This contradiction is known as the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The Fermi Paradox has inspired numerous hypotheses, ranging from the idea that intelligent civilizations are extremely rare to the possibility that advanced life intentionally avoids contact with us. Some theories suggest that civilizations may tend to self-destruct before achieving interstellar travel, or that advanced societies might exist in forms that we cannot perceive or understand. Others propose that intelligent life is common but remains hidden to avoid detection, a concept known as the zoo hypothesis, where Earth is intentionally isolated. The search for extraterrestrial intelligence, SETI, has expanded our understanding of the universe and introduced innovative techniques for detecting potential signals. Researchers now explore various wavelengths, including radio and optical, and analyze signals for patterns that could indicate artificial origins. Despite the silence, the Fermi Paradox continues to drive our curiosity, urging us to consider not only the possibility of life beyond Earth, but also our place in the universe. The Fermi Paradox raises profound questions about life, intelligence, and the nature of civilizations. It challenges us to reflect on our own future as a species and consider whether we are truly alone in the vastness of space, or simply not yet ready to understand the answers. Cosmic inflation: the universe's rapid expansion. Cosmic inflation is the theory that, within the first fractions of a second after the Big Bang, the universe underwent an incredibly rapid expansion, growing faster than the speed of light. This expansion stretched quantum fluctuations to cosmic scales, seeding the formation of galaxies, stars, and other structures we see today. Proposed by physicist Alan Guth in the 1980s, inflation explains several key mysteries of cosmology, such as why the universe appears so uniform, and why distant regions have similar temperatures despite being far apart. During inflation, the universe expanded exponentially, increasing in size by a factor of trillions in an instant.
32 seconds
This
into the
process
flight.
flattened the curvature of space-time,
Liquid fuel
leading
main
to the
engines
large-scale
will throttle back to
uniformity observed in the
72% of rated
cosmic
performance down
microwave
in the bucket,
background.
reducing the stress on the
Inflation
shuttle as
also
it goes
smoothed out
transonic.
any irregularities, setting the stage for a universe that appears largely homogeneous but contains the subtle density fluctuations that gave rise to galaxies and clusters. The theory of inflation also raises intriguing possibilities about the multiverse. Some models suggest that inflation may not have stopped everywhere, resulting in a bubble structure where new universes form in different regions. In this view, our observable universe is just one of countless bubbles created by an eternal inflationary process. Cosmic inflation reshapes our understanding of the universe's origins, suggesting that the Big Bang was not a singular event but part of a larger cosmic process. It provides a framework for explaining the structure and evolution of the cosmos, offering a glimpse into the forces that shaped the universe from its very first moments. Quantum entanglement: the universe's mysterious connection. Quantum entanglement is a phenomenon where particles become connected in such a way that the state of one particle instantly influences the state of another, no matter how far apart they are. First described by Albert Einstein as spooky action at a distance, entanglement defies classical notions of locality and suggests a fundamental interconnectedness at the quantum level. In entanglement, pairs of particles share a common quantum state. When one particle is measured, its entangled partner adopts a complementary state, even if it is light years away. This effect occurs instantaneously, seemingly violating the speed limit set by the speed of light. While entanglement has been confirmed through experiments, its implications remain mysterious, challenging our understanding of reality and the nature of information. Entanglement plays a central role in emerging fields like quantum computing and quantum cryptography. In quantum computers, entangled particles, qubits, enable calculations that far surpass the capabilities of classical computers. Quantum cryptography uses entanglement to create secure communication channels, with any attempt at eavesdropping disrupting the entangled state. The phenomenon of entanglement raises questions about the nature of information and the structure of space-time. Some theories suggest that entanglement may be the glue that holds space-time together, connecting distant regions and creating a hidden structure beneath our observable reality. Quantum entanglement challenges us to rethink the boundaries of knowledge, offering glimpses of a reality where everything is profoundly connected. The observable universe and its horizon. The observable universe refers to the portion of the cosmos from which light has had time to reach us since the Big Bang, limited by the speed of light and the universe's age. This region, with a radius of about 46 billion light-years, contains all the stars, galaxies, and cosmic structures we can study. Beyond this cosmic horizon lies an unknown realm, where light has yet to reach us, and the true scale of the universe remains hidden. The observable universe's boundary is not fixed. It expands as light from more distant regions reaches us over time. However, because the universe's expansion is accelerating, some galaxies are moving away so quickly that their light may never reach us, effectively placing them beyond our observational reach forever. The cosmic horizon also raises questions about what lies beyond. If the universe is infinite, there could be countless galaxies and structures extending indefinitely. Some theories suggest that beyond the observable universe, physical laws or constants might vary, creating regions that differ fundamentally from our own. This idea forms the basis for some multiverse theories, where our universe is one of many with unique properties. The concept of the observable universe highlights the limits of human knowledge, marking the boundary between what we can study and what lies forever beyond. It challenges us to confront the vastness of cosmic time and space, reminding us that even the largest structures we observe may be only a small fraction of an incomprehensibly larger reality. Neutrinos, the ghostly particles of the universe. Neutrinos are nearly massless particles that travel close to the speed of light and rarely interact with ordinary matter. Known as ghost particles, neutrinos are produced in enormous quantities by nuclear reactions within stars, supernovae, and other high-energy cosmic events. Despite being one of the most abundant particles in the universe, neutrinos are incredibly difficult to detect, as they pass through most matter undisturbed. Neutrinos were first theorized in the 1930s to explain missing energy in radioactive decay. Today, they are a critical part of particle physics, with three known types: electron neutrinos, muon neutrinos, and tau neutrinos. Neutrinos have also been detected from sources like the Sun, nuclear reactors, and supernova 1987A, the first supernova observed to emit detectable neutrinos. Because neutrinos rarely interact with matter, they provide unique insights into processes that would otherwise remain hidden. Neutrino observatories, like the IceCube Neutrino Observatory in Antarctica, detect these elusive particles, offering a new way to study supernovae, gamma-ray bursts, and other cosmic phenomena. Neutrinos also help scientists probe the fundamental properties of matter and the universe's evolution. The study of neutrinos challenges us to explore the hidden aspects of reality, revealing that even the smallest particles can carry information across vast cosmic distances. Neutrinos remind us that the universe is filled with invisible connections, where particles move through the cosmos, carrying secrets about its deepest mysteries. Gamma-ray bursts, the most powerful explosions in the universe. Gamma-ray bursts, GRBs, are the most energetic explosions in the cosmos, releasing more energy in a few seconds than our Sun will produce over its entire lifetime. These bursts are classified into two types: short-duration bursts lasting less than 2 seconds, and long-duration bursts lasting more than 2 seconds. Both types are incredibly powerful, emitting intense gamma-ray radiation, the highest energy form of light. Scientists believe that long-duration GRBs occur when massive stars collapse into black holes, releasing jets of energy that can be seen across billions of light-years. Short-duration GRBs are thought to result from the collision of neutron stars or a neutron star merging with a black hole, a phenomenon also capable of producing gravitational waves. Observing GRBs provides insights into the death of massive stars, the formation of black holes, and the processes driving the most extreme cosmic events. Gamma-ray bursts are critical for understanding the early universe. Because they are so bright, GRBs can be detected at vast distances, allowing astronomers to study stars and galaxies that existed only a few 100 million years after the Big Bang. By analyzing the light from GRBs, scientists gather clues about the composition and evolution of the universe at a time when galaxies were first forming. The study of GRBs has practical implications as well. These intense bursts of energy pose a potential risk to life on Earth if one were to occur close enough. Fortunately, known GRBs are located at safe distances, but studying their mechanisms helps scientists assess cosmic threats and develop strategies for future observations. The holographic principle. Is the universe a projection? The holographic principle is a revolutionary idea suggesting that all the information within a three-dimensional space, like our universe, can be encoded on a two-dimensional surface. This concept arises from studies of black holes, where physicists realize that the information content of a black hole, its entropy, is proportional to its surface area, not its volume. This insight led to the hypothesis that the entire universe might function like a hologram, where the three-dimensional world we experience is a projection of information stored on a two-dimensional boundary. The holographic principle has profound implications for our understanding of reality and the nature of space-time. If true, it would mean that our perception of depth and space might be an illusion, with the true nature of reality existing in a lower dimensional space. This idea is supported by certain theories in string theory and quantum gravity, which suggest that the universe could be fundamentally composed of information. In the context of cosmology, the holographic principle could offer solutions to long-standing paradoxes, such as the black hole information paradox. It also suggests that gravity might be an emergent property, a phenomenon that arises from the interactions of information on a lower dimensional surface. This idea remains speculative, but it continues to inspire research into the nature of information, reality, and the relationship between quantum mechanics and general relativity. The holographic principle challenges us to rethink our understanding of space, time, and existence. It suggests that the universe may be more interconnected than we realize, with every particle, field, and force ultimately linked by the fabric of information itself. White holes, theoretical opposites of black holes. White holes are hypothetical objects that are the reverse of black holes. While a black hole pulls everything in with its intense gravity, a white hole would theoretically expel matter and energy, allowing nothing to enter. White holes are solutions to Einstein's field equations, yet they remain purely theoretical, as no observational evidence of their existence has been found. Some scientists suggest that white holes could represent the other side of a black hole, where matter falling into a black hole in one part of the universe emerges from a white hole in another part. This idea is linked to certain interpretations of the wormhole concept, where black holes and white holes are connected by a tunnel through space-time. Such a connection could theoretically allow for faster-than-light travel across vast distances. White holes are also considered in certain models of quantum gravity, where they might provide a mechanism for escaping the information paradox. If information is preserved as it falls into a black hole, a white hole could potentially release that information back into the universe. This concept is purely speculative, but it represents one of the many ways scientists explore the boundaries of physics and the nature of reality. While no evidence for white holes exists, their theoretical implications push the limits of our understanding of space-time, suggesting that black holes might not be the final word in the study of extreme gravitational phenomena. White holes remind us that the cosmos is filled with possibilities, some of which challenge our deepest assumptions about the nature of existence. Cosmic rays and high-energy particles. Cosmic rays are high-energy particles that travel through space and originate from sources like supernovae, neutron stars, and active galactic nuclei. These particles, primarily protons and atomic nuclei, move at nearly the speed of light and have energies far greater than those produced by human-made particle accelerators. When cosmic rays collide with Earth's atmosphere, they create showers of secondary particles, some of which reach the ground. Cosmic rays were first discovered in the early 20th century and have been studied ever since to understand their origins and effects on Earth. Some of the highest energy cosmic rays, known as ultra-high energy cosmic rays, are still a mystery, as their sources remain unidentified. These particles provide clues about extreme environments in the universe, where particles are accelerated to unimaginable energies. Cosmic rays also impact technology and human health. High-energy particles can penetrate spacecraft, posing a risk to astronauts on deep space missions. Cosmic rays also affect electronic systems, particularly in high-altitude flights, and can lead to bit flips in computer memory. Studying cosmic rays helps scientists understand the conditions in space and develop protective measures for future space exploration. Cosmic rays remind us that the universe is a dynamic place filled with energetic phenomena. These particles, traveling across vast distances, carry information about the cosmos's most extreme environments, providing a link between Earth and the far reaches of space. The heat death of the universe. The end of time. The heat death is a theoretical scenario describing the universe's ultimate fate if it continues expanding indefinitely. In this model, the universe will reach a state of maximum entropy, where all energy is evenly distributed, and no usable energy remains to power processes like star formation, motion, or even life. Over an unimaginable timescale, stars will burn out, galaxies will drift apart, and black holes will eventually evaporate due to Hawking radiation, leaving a dark, cold cosmos. The heat death scenario, also known as the Big Freeze, arises from the second law of thermodynamics, which states that entropy or disorder always increases in a closed system. As the universe expands, it becomes increasingly isolated, with less potential for energy to perform work. Once all matter decays and energy is evenly distributed, the universe will reach a state of thermal equilibrium, where no further change is possible. This vision of the universe's end is bleak, as it implies a future without life, motion, or complexity. However, it also raises philosophical questions about time and existence. If the universe reaches a state where nothing changes, does time still have meaning? In a state of maximum entropy, where no events occur, the concept of time may lose its significance. The heat death of the universe challenges us to confront the limits of cosmic evolution. It suggests that, despite the complexity and beauty we observe in the universe today, the cosmos may ultimately settle into a state of quiet stillness, where the passage of time itself fades into insignificance. The Kardashev scale, measuring civilizations by cosmic power. The Kardashev scale, proposed by astrophysicist Nikolai Kardashev in 1964, is a hypothetical framework for measuring the technological advancement of civilizations based on their energy consumption. The scale is divided into three main types, each representing a civilization's mastery over different energy sources. Type I civilizations harness the energy of their home planet, controlling resources like solar, wind, and geothermal energy to power their needs. Humanity is currently around Type 0.7 on this scale, still largely reliant on fossil fuels and limited in its energy management capabilities. Type I civilizations control the energy of their entire star, possibly by constructing massive structures like Dyson spheres to capture stellar energy. Such a civilization would have energy capabilities far beyond anything we can imagine, allowing for advanced space exploration, mega engineering projects, and potentially interstellar travel. Type I civilizations harness the energy of their entire galaxy, controlling stars and other celestial bodies. These civilizations would possess knowledge and technology far beyond our understanding, potentially mastering energy at cosmic scales. A Type I civilization would likely have encountered other advanced civilizations and might even explore or influence other galaxies. The Kardashev scale encourages us to think about the future of humanity and our place in the cosmos. While the concept remains speculative, it highlights the potential for technological advancement and the energy challenges we must overcome. The scale reminds us that, in a universe filled with possibility, civilizations may reach levels of power and influence that transcend our current understanding. Actions and dark matter candidates. Actions are hypothetical particles that could be the building blocks of dark matter, the mysterious substance that makes up about 27% of the universe. Originally proposed to solve a problem in particle physics known as the strong CP problem, actions have since become one of the leading candidates for dark matter. These particles are predicted to be extremely light and weakly interacting, making them difficult to detect. Unlike WIMPs, weakly interacting massive particles, another dark matter candidate, actions would interact primarily through the electromagnetic field. If actions exist, they might convert into photons, particles of light, in the presence of a strong magnetic field. This property has led scientists to design experiments like the Action Dark Matter Experiment and MEX to detect potential action signals. Actions represent an exciting frontier in dark matter research. Discovering them would not only solve one of the major puzzles in particle physics, but also reveal the true nature of dark matter, providing answers to the questions surrounding the universe's missing mass. If actions are detected, they could transform our understanding of particle physics and cosmology, helping us build a more complete picture of the universe. The search for actions challenges us to think beyond visible matter and consider the hidden forces shaping the cosmos. Whether or not actions prove to be dark matter, their study exemplifies the ongoing quest to uncover the universe's secrets. The cosmological constant and the mystery of dark energy. The cosmological constant, initially introduced by Albert Einstein in his equations of general relativity, represents the energy density of empty space. While Einstein later discarded it as a blunder after discovering that the universe was expanding, the concept resurfaced with the discovery of dark energy in the late 1990s. Today, the cosmological constant is one of the leading explanations for dark energy, a mysterious force driving the accelerated expansion of the universe. Dark energy comprises approximately 68% of the universe, influencing its structure and evolution. If the cosmological constant indeed represents dark energy, it suggests that the energy density of space remains constant even as the universe expands. This constant energy density creates a repulsive force, counteracting gravity on cosmic scales and causing galaxies to move away from each other at an accelerating rate. The nature of the cosmological constant remains one of the greatest mysteries in physics. Theoretical predictions of its value differ vastly from observed measurements, leading to the cosmological constant problem. Solving this discrepancy may require new physics, potentially shedding light on the interaction between quantum mechanics and gravity. Understanding the cosmological constant could reveal fundamental aspects of space, time, and the fate of the universe itself. The cosmological constant challenges our understanding of the fabric of reality, suggesting that space is not empty but filled with energy. It reminds us that the universe is governed by forces we have yet to fully comprehend, inviting us to explore the mysteries of dark energy and the ultimate destiny of the cosmos. Primordial black holes, remnants from the early universe. Primordial black holes are hypothetical black holes that may have formed shortly after the Big Bang, during a period of extreme density and temperature. Unlike stellar black holes, which are formed by collapsing stars, primordial black holes could have originated from density fluctuations in the early universe, collapsing under their own gravity. These black holes might range in size from tiny subatomic particles to massive objects several times the mass of the Sun. If primordial black holes exist, they could account for a portion of dark matter, as they would be invisible except for their gravitational effects. Detecting these objects could reveal valuable insights into the early universe and the formation of cosmic structures. Some researchers have proposed that certain gravitational wave signals observed by detectors like LIGO and Virgo could be due to the collision of primordial black holes, offering indirect evidence for their existence. Primordial black holes could also influence the evolution of galaxies and stars. If located within galaxies, they could serve as seeds for supermassive black holes, providing the initial mass necessary to grow through accretion. Understanding primordial black holes could bridge the gap between cosmology and particle physics, offering clues about the universe's first moments and the role of dark matter in cosmic evolution. The search for primordial black holes challenges us to explore the limits of our theories about the universe's origins. These ancient objects, if they exist, would be relics of a time when the cosmos was governed by forces and densities beyond our current understanding. The Great Filter, a hypothetical explanation for the Fermi paradox. The Great Filter is a concept proposed to explain the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for advanced civilizations. The Great Filter suggests that there may be a rare, challenging hurdle or series of hurdles that prevents life from evolving into an advanced, space-faring civilization. This filter could occur at any stage of a civilization's development. It may lie in the transition from simple organisms to complex life, or from intelligent life to technologically advanced societies. Some believe the filter could lie ahead of us, in the form of challenges like resource depletion, self-destruction, or environmental collapse. If the Great Filter is behind us, it would mean humanity has already passed a rare barrier. If it lies ahead, it suggests that achieving a long-term space-faring civilization may be more difficult than we realize. The Great Filter raises profound questions about our future as a species. It challenges us to consider whether humanity can overcome the obstacles that may have prevented other civilizations from reaching the stars. By reflecting on the Great Filter, we gain perspective on the importance of cooperation, sustainability, and the pursuit of knowledge as we continue our journey into the cosmos. The Great Filter reminds us of our unique position in the universe and our responsibility to preserve and advance civilization. It invites us to explore the challenges that lie ahead, not only for ourselves but for the potential future of intelligent life beyond Earth. The EPR paradox and quantum reality. The EPR paradox, named after physicists Einstein, Podolsky, and Rosen, is a thought experiment that challenges the completeness of quantum mechanics. In 1935, Einstein and his colleagues argued that if quantum mechanics were correct, it would allow for spooky action at a distance, where measuring the state of one particle could instantaneously affect another, regardless of the distance between them. This concept is known today as quantum entanglement. The EPR paradox highlights a fundamental tension between quantum mechanics and classical notions of reality. According to quantum theory, entangled particles remain connected no matter how far apart they are, meaning that a change in one particle instantly reflects in the other. This non-local connection seems to violate the principle that nothing can travel faster than light, challenging the foundations of relativity. In the 1960s, physicist John Bell developed an inequality, known as Bell's theorem, to test whether hidden variables could explain quantum correlations. Experiments to test Bell's theorem have shown that entangled particles exhibit correlations that cannot be explained by any local hidden variables, supporting the idea that quantum mechanics is inherently non-local. The EPR paradox has led to new fields of research, such as quantum information science, which seeks to harness entanglement for technologies like quantum computing and secure communication. It also raises questions about the nature of information, reality, and the limits of human knowledge. The EPR paradox reminds us that the universe may operate in ways that defy classical logic, revealing a deeper interconnectedness between particles, information, and reality itself. The Pioneer Anomaly, a cosmic mystery. The Pioneer Anomaly refers to an unexpected deviation in the trajectories of NASA's Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s to explore the outer solar system. After passing beyond the orbits of the outer planets, both probes began to experience a small, consistent acceleration toward the Sun, puzzling scientists and sparking debate about the nature of this mysterious force. The anomaly was subtle, an acceleration of only about 8.74 x 1010 m s2, yet it persisted over decades, leading some researchers to question whether it could indicate new physics or unknown forces. Some speculated that dark matter, modifications to Newtonian gravity, or even the influence of exotic particles might explain the effect. Others suggested that thermal radiation from the spacecraft could be responsible, as the heat emitted unevenly from the probes could create a small but consistent push. After extensive study, researchers eventually concluded that the anomaly was likely due to asymmetric thermal radiation, as heat from the probe's power sources created a subtle, consistent thrust in the direction opposite their motion. This explanation, however, does not diminish the significance of the Pioneer anomaly, as it highlighted the need for precision in understanding the forces acting on spacecraft as they journey through space. The Pioneer anomaly reminds us of the challenges and uncertainties of space exploration. Even small, unexplained forces can impact our understanding of the cosmos, revealing gaps in our knowledge and inspiring new investigations. This mystery, though largely resolved, serves as a reminder that the universe is filled with subtle phenomena that can challenge our understanding of physics, encouraging scientists to approach the cosmos with curiosity and rigor. The Pioneer anomaly is a testament to humanity's desire to explore and understand, as well as to the precision required in studying the cosmos. It represents the unexpected questions that arise when we push the boundaries of exploration, revealing the complex interactions between matter, energy, and space itself. Primordial black holes, relics from the early universe. Primordial black holes, PB8s, are hypothetical black holes thought to have formed shortly after the Big Bang, during the universe's earliest moments. Unlike black holes formed from collapsing stars, which require a significant amount of time and massive stars, primordial black holes could have formed from regions of extremely high density in the young universe, created by fluctuations in matter distribution. These regions, compressed by gravity, might have collapsed into black holes just a fraction of a second after the Big Bang. Primordial black holes could vary widely in size, from tiny micro-black holes, smaller than an atom, to larger ones with masses comparable to mountains or even small planets. Their formation would depend on specific conditions in the early universe, where density fluctuations would need to be strong enough to overcome cosmic expansion, but not so intense as to prevent the universe's subsequent structure formation. One of the fascinating possibilities surrounding primordial black holes is their potential role as dark matter candidates. Dark matter, which constitutes about 27% of the universe's mass and energy, does not emit or absorb light, making it invisible and detectable only through its gravitational effects. If primordial black holes exist in large enough numbers, they could account for at least a portion of dark matter, as their gravitational pull could explain the missing mass observed in galaxies and clusters. Detecting primordial black holes is challenging, as they do not emit light and are expected to be scattered sparsely throughout the cosmos. However, several methods have been proposed to search for them. One approach involves looking for the gravitational lensing effects caused by primordial black holes passing in front of stars, temporarily brightening them as the black hole's gravity bends the starlight. Another method is searching for signs of Hawking radiation, as very small primordial black holes are expected to emit this radiation, slowly losing mass and eventually evaporating in a final burst of energy. If primordial black holes were to be discovered, they would offer an unprecedented window into the conditions of the early universe. These ancient objects could provide insights into the physics of high-energy density environments and help us understand the formation of cosmic structures. Moreover, they would bridge the gap between particle physics and cosmology, revealing how microscopic fluctuations in the primordial universe can lead to massive objects that endure billions of years. Primordial black holes remind us that the universe may hold remnants from its earliest moments, preserved as relics of the Big Bang. They represent the intersection of theory and observation, where the most ancient and enigmatic phenomena still exert a gravitational influence on the cosmos today. By studying them, we would gain clues about the universe's origin, its evolution, and the fundamental nature of matter and gravity. The fine-tuned universe, a question of cosmic coincidence. The concept of a fine-tuned universe refers to the observation that the fundamental physical constants and laws appear to be set at values that allow for the existence of complex structures, stars, planets, and, ultimately, life. If these constants were even slightly different, the universe would be vastly different, possibly incapable of supporting any form of complexity or life. This apparent fine-tuning raises questions about why the universe's laws seem so precisely calibrated. There are many examples of fine-tuning in the universe. For instance, the strength of the gravitational force, if only slightly weaker, would prevent galaxies, stars, and planets from forming. Conversely, if it were stronger, stars would burn their fuel too quickly for life to evolve. Similarly, the ratio of protons to electrons is precisely balanced, ensuring that the universe is electrically neutral on a large scale, which is essential for stable atomic and molecular structures. Another example is the cosmological constant, a parameter that describes the energy density of empty space and is linked to dark energy. If this constant were larger, the accelerated expansion of the universe would prevent galaxies from forming. If it were smaller, the universe could have collapsed under its own gravity shortly after the Big Bang. The narrow range within which the cosmological constant appears to fall is so specific that some scientists liken it to balancing a pencil on its tip, requiring an extraordinary level of precision. The fine-tuning of the universe has led to various interpretations. One possibility is the anthropic principle, which suggests that we observe these conditions because we exist within them. In other words, the universe appears fine-tuned because only a universe with such properties could support observers like us. Another explanation is the multiverse theory, which posits that there may be countless universes with different physical constants and laws. In this view, our universe is one of the few where the constants happen to allow for life, making it an observational coincidence. The idea of a fine-tuned universe raises questions about the nature of reality and whether there is an underlying purpose or cause for these precise values. Some propose that this fine-tuning could suggest the existence of a creator or an intelligent designer, while others argue that it could simply be a byproduct of natural processes or quantum fluctuations. The fine-tuning debate intersects with philosophy, cosmology, and theology, each offering different perspectives on why the universe appears as it does. Fine-tuning reminds us of the delicacy and interconnectedness of the universe's forces and constants. It suggests that the cosmos is not random but operates within a narrow range of possibilities that allow for complexity and consciousness. Whether by coincidence, necessity, or design, the fine-tuning of the universe continues to be one of the most profound mysteries, challenging us to ponder the origins and nature of reality itself. Fast radio bursts, the mysterious signals from deep space. Fast radio bursts, FRBs, are intense, brief pulses of radio waves originating from distant galaxies. Lasting only milliseconds, these bursts release an enormous amount of energy, equivalent to the sun's output in an entire day. Discovered in 2007, FRBs have become one of the most intriguing phenomena in astronomy, sparking a wide range of theories about their origins, from neutron stars to alien civilizations. Most FRBs are one-time events, known as non-repeating FRBs, which makes pinpointing their sources challenging. However, a small number of FRBs have been observed to repeat from the same location, allowing scientists to study them in greater detail. These repeating FRBs come from locations in galaxies that suggest association with magnetars, a type of neutron star with an exceptionally strong magnetic field. The exact mechanism behind FRBs remains unknown, but the involvement of magnetars is one of the leading hypotheses. FRBs are detected by radio telescopes, which scan the sky for transient signals. One of the most significant discoveries in recent years is FREB 121-102, a repeating FREB located in a distant dwarf galaxy. Its periodic bursts of energy have allowed astronomers to study its source, suggesting that the environment surrounding FREB 121-102 is highly magnetized, likely due to a nearby magnetar or an active galactic nucleus. This intense environment might be responsible for the energetic processes that produce these bursts. Another fascinating aspect of FRBs is their dispersion measure, which is the degree to which radio waves are scattered by intergalactic plasma. This scattering provides a rough estimate of the distance between the source and Earth, making FRBs valuable tools for mapping the distribution of matter in the universe. By studying the dispersion of FRBs from different regions, scientists can learn about the density of intergalactic plasma and the distribution of matter on cosmic scales. Some researchers have speculated that FRBs could be artificial in origin, potentially signals from advanced extraterrestrial civilizations. While there is currently no evidence to support this idea, the sheer energy and precision of FRBs have fueled imaginations. However, most astronomers believe that natural astrophysical processes are responsible, as the mechanisms involving neutron stars and magnetars can account for the observed properties of FRBs. The study of FRBs is still in its infancy, yet each new discovery brings us closer to understanding these enigmatic bursts. They reveal the energetic and dynamic nature of the universe, showing that even brief, fleeting events can carry vast amounts of information about cosmic environments. FRBs challenge our understanding of astrophysics, hinting at processes and objects that operate at the limits of known science. Dark flow, a mysterious motion beyond the cosmic horizon. Dark flow is an unusual phenomenon observed in the motion of galaxy clusters, suggesting that they are moving in a consistent direction at velocities that cannot be fully explained by the expansion of the universe alone. Discovered in 2008 through studies of the cosmic microwave background, CMB, dark flow appears to involve clusters moving toward a specific region of the sky, hinting at an influence from beyond the observable universe. The concept of dark flow challenges the standard cosmological model, which assumes that matter and energy are evenly distributed on the largest scales, resulting in no large-scale directional flow. However, measurements of galaxy cluster motions using the Sunyaev-Zeldovich effect and interaction between the CMB and hot gas in galaxy clusters indicate a motion that aligns across hundreds of millions of light years, directed toward the constellations Centaurus and Hydra. One possible explanation for dark flow is the gravitational influence of a massive structure beyond the cosmic horizon, potentially a supervoid or a supercluster larger than anything observed within the observable universe. Such a structure, if it exists, would lie beyond the reach of current telescopes, making it detectable only through its gravitational effects on observable matter. The existence of dark flow has sparked debates among cosmologists, as it could imply that the universe is not homogeneous on the largest scales. Instead, dark flow suggests that the universe may be part of a larger, interconnected structure, with regions beyond our cosmic horizon exerting influence on matter within our observable universe. Some researchers propose that dark flow could even be evidence for the multiverse, where neighboring universes or regions with different physical properties could exert a gravitational pull on our own universe. If these hypothetical neighboring universes exist, they might create gravitational effects that influence the motion of galaxy clusters within our observable realm, subtly tugging them in a particular direction. The idea of dark flow is controversial and still under investigation. Some studies have questioned the initial findings, suggesting that dark flow may not be as pronounced as originally thought, or that it could be explained by statistical anomalies. However, if dark flow is real, it represents a significant puzzle, as it challenges the cosmological principle, the idea that the universe is uniform on the largest scales. Dark flow implies that our universe might be influenced by structures or forces beyond the observable cosmos, raising profound questions about the nature of reality and the potential existence of realms we cannot see. Further research into dark flow will require more detailed observations of the cosmic microwave background and galaxy clusters across vast distances. Upcoming space missions, such as the Euclid and Nancy Grace Roman Space Telescopes, may provide insights into the distribution of matter and the potential existence of dark flow. By studying these large-scale movements, scientists hope to understand whether the dark flow is a real phenomenon or simply a statistical artifact. Dark flow reminds us that the universe may hold hidden structures and forces that lie beyond our current understanding. It challenges the boundaries of observational cosmology, suggesting that the universe we observe may be influenced by phenomena far outside our reach. Whether dark flow is an anomaly or a hint of a larger cosmic framework, it serves as a reminder that the universe is filled with mysteries that may stretch beyond the limits of our observable horizon. Vacuum energy and the mystery of dark energy. Vacuum energy is the energy present in empty space, even in the absence of matter or radiation. According to quantum mechanics, the vacuum is not truly empty, but is filled with fluctuating virtual particles that briefly pop into and out of existence. These fluctuations give rise to a tiny amount of energy known as vacuum energy, which contributes to the overall dynamics of the universe. This concept of vacuum energy is closely linked to dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up roughly 68% of the universe's total energy content, yet its nature remains one of the most profound mysteries in cosmology. Discovered in the late 1990s through observations of distant supernovae, dark energy appears to be causing galaxies to move apart at an increasing rate. This discovery revolutionized our understanding of the cosmos, suggesting that the universe's fate may be determined by a force that counteracts gravity on the largest scales. One leading hypothesis is that dark energy is a manifestation of vacuum energy. In this view, the energy of the vacuum exerts a negative pressure that accelerates the expansion of space. However, calculations of vacuum energy based on quantum field theory predict an energy density that is vastly higher than what is observed, leading to a discrepancy known as the cosmological constant problem. This mismatch between theoretical predictions and observations remains one of the biggest challenges in theoretical physics. Alternative explanations for dark energy include quintessence, a hypothetical scalar field that varies over time and space. Unlike vacuum energy, which is constant, quintessence would change as the universe evolves, potentially leading to different rates of expansion at different epochs. This concept aligns with some theories of modified gravity, which suggest that the laws of gravity may differ on cosmic scales, creating effects that resemble the influence of dark energy. Understanding dark energy and vacuum energy could have profound implications for the future of the universe. If dark energy remains constant, the universe will continue to expand indefinitely, leading to the Big Freeze scenario, where galaxies drift apart, stars burn out, and the universe becomes cold and dark. If dark energy changes over time, it could lead to alternative scenarios, such as the Big Rip, where dark energy eventually tears apart galaxies, stars, and even atoms themselves. Vacuum energy and dark energy remind us that even empty space is filled with mysteries. They challenge our understanding of the nature of space, time, and gravity, suggesting that the universe operates under principles that are still beyond our grasp. As scientists continue to probe the cosmos, the study of dark energy and vacuum energy may reveal new aspects of reality, reshaping our understanding of the universe and its ultimate fate. Time dilation and the twin paradox. Time dilation is a phenomenon predicted by Einstein's theory of relativity, where time passes at different rates depending on an object's speed or gravitational field. According to special relativity, as an object approaches the speed of light, time slows down for it relative to a stationary observer. This effect is known as time dilation due to relative velocity, and it has been confirmed by experiments with particles traveling at near light speeds, as well as by atomic clocks on high-speed aircraft and satellites. One of the most famous thought experiments involving time dilation is the twin paradox, where one twin travels on a high-speed journey through space, while the other remains on Earth. Upon returning, the traveling twin would find that they have aged more slowly than their sibling due to the effects of time dilation. Although it may seem counterintuitive, this phenomenon has been confirmed by experimental evidence and forms a cornerstone of modern physics. Time dilation also occurs in the presence of strong gravitational fields, an effect predicted by general relativity. Near massive objects like black holes, gravity warps space-time to such an extent that time passes more slowly. This phenomenon, known as gravitational time dilation, has been observed through experiments involving GPS satellites, which must account for both gravitational and velocity-based time dilation to provide accurate positioning data on Earth. The closer a clock is to a massive object, the slower it ticks, leading to measurable differences in time. The implications of time dilation extend to space travel and our understanding of the universe's structure. If humans were to embark on interstellar journeys at near light speeds, they could experience significant time dilation, effectively traveling into the future relative to those who remain on Earth. This concept has inspired science fiction stories and theoretical discussions about the nature of time, highlighting the flexibility and relativity of temporal experience. Time dilation also influences our understanding of the universe's evolution. In the vicinity of black holes and other dense objects, time dilation affects the rate at which matter falls into these objects, creating observable differences in how they grow and interact with their surroundings. Gravitational time dilation near the event horizon of a black hole, for example, means that an object falling toward the black hole would appear to slow down in redshift, eventually freezing in time from the perspective of a distant observer. The study of time dilation reminds us that time is not an absolute uniform flow, but is instead shaped by motion and gravity. It challenges our perceptions of reality, suggesting that time is flexible, and that our experience of it depends on our position and velocity within space-time. Time dilation reveals the complexity of the cosmos, where even the flow of time is influenced by the universe's forces and structures. The anthropic principle and the question of purpose. The anthropic principle is a philosophical consideration that attempts to explain why the universe's physical constants and laws appear to be fine-tuned for life. In its simplest form, the anthropic principle suggests that the universe must have properties that allow for the existence of observers, as we are here to observe it. This principle comes in two primary forms: the weak anthropic principle, which states that we can observe only a life-permitting universe, and the strong anthropic principle, which implies that the universe's properties may be inherently life-friendly. The anthropic principle arises from the observation that small changes in fundamental constants, such as the strength of gravity or the electromagnetic force, would render the universe inhospitable to life. If gravity were slightly stronger, stars would burn out too quickly, while if it were weaker, galaxies might never form. Similarly, the balance between matter and antimatter, the properties of subatomic particles, and the expansion rate of the universe are all finely tuned in ways that seem conducive to life. Some interpret the anthropic principle as evidence of design or purpose, suggesting that the universe's life-friendly properties are not coincidental but intentional. This interpretation often overlaps with theological or philosophical arguments, positing that the universe may have been created with life in mind. Others argue that the anthropic principle is simply a result of observational bias. We observe a life-permitting universe, because only such a universe could contain observers like ourselves. The anthropic principle also intersects with the multiverse theory, which posits that our universe may be one of many, each with different physical laws and constants. In a multiverse, it is conceivable that only a small fraction of universes have properties compatible with life. We happen to exist in one of those few universes, leading to the appearance of fine-tuning. This perspective suggests that our universe's properties are not unique, but are instead part of a vast ensemble, where countless other universes may exist with entirely different characteristics. The anthropic principle invites reflection on the nature of existence and the reasons behind the universe's properties. It challenges us to consider whether life and consciousness are fundamental outcomes of cosmic evolution or merely incidental byproducts. The anthropic principle is a reminder that the universe's structure and laws are delicately balanced, inviting questions about purpose, randomness, and the potential for deeper underlying principles. The holographic principle. Is the universe a projection? The holographic principle is a theory that suggests all the information contained within a volume of space can be represented on its boundary, much like a hologram. In this view, our three-dimensional universe could be a projection from a two-dimensional surface, where the information defining everything we experience is encoded. This radical idea challenges our understanding of space, matter, and reality, suggesting that the universe might not be what it appears to be. The holographic principle emerged from attempts to understand black holes and the paradoxes associated with them, specifically the black hole information paradox. According to classical physics, anything that falls into a black hole is lost beyond the event horizon, seemingly erasing information. However, quantum mechanics dictates that information should be conserved. To resolve this paradox, physicists proposed that information about the contents of a black hole might be stored on its event horizon, leading to the idea that a two-dimensional surface could encode the properties of three-dimensional objects. The holographic principle was later extended to the entire universe, suggesting that our reality could be a projection from a two-dimensional boundary in a higher dimensional space. This concept has been explored through string theory, where certain mathematical models support the idea that a lower dimensional boundary can contain all the information needed to describe a higher dimensional space. In these models, the universe behaves like a hologram, with everything we perceive as three-dimensional actually being encoded on a distant, two-dimensional surface. One fascinating implication of the holographic principle is that it could help reconcile quantum mechanics and general relativity. In a holographic universe, gravity emerges as a result of the interactions on the boundary, potentially offering a new way to understand gravity within the framework of quantum mechanics. This approach, known as the AT-CFT correspondence, anti-de Sitter conformal field theory, has provided insights into black holes, entanglement, and the nature of space-time itself. While the holographic principle remains theoretical, experimental research is underway to explore its implications. Some physicists are investigating whether the structure of space-time at the quantum level resembles a holographic encoding, with phenomena like entanglement revealing how information is shared across space. This research raises the possibility that our universe is fundamentally informational, with matter, energy, and space-time all emerging from a deeper, underlying code. The holographic principle invites us to question the nature of reality, challenging the assumption that the universe we perceive is the true reality. It suggests that what we experience is solid. Physical matter may ultimately be an illusion, a projection from a lower dimensional realm. This concept offers a radical perspective on existence, blurring the lines between the tangible and the abstract, and reminding us that the universe may be more complex and interconnected than we can currently comprehend. The Alcubierre warp drive, faster than light travel. The Alcubierre warp drive is a theoretical concept that proposes a way to achieve faster than light travel without violating the laws of physics, particularly Einstein's theory of relativity. Named after Mexican physicist Miguel Alcubierre, who introduced the idea in 1994, the warp drive relies on the concept of space-time manipulation rather than traditional propulsion. Instead of moving through space, the warp drive would create a bubble of warped space-time around a spacecraft, contracting space in front of it and expanding space behind it. In this warp bubble, the spacecraft itself would remain stationary relative to the space within the bubble, allowing it to move faster than light without technically exceeding the speed limit set by relativity. This approach sidesteps the problem of traveling through space at superluminal speeds, as the spacecraft would not be moving through space in the conventional sense, but would instead be carried along by the manipulated fabric of space-time itself. The idea of a warp drive is inspired by the mathematics of general relativity, which allows for the theoretical manipulation of space-time. However, creating a warp bubble would require an immense amount of energy, specifically a form of negative energy or exotic matter with properties that are not yet understood or available. Negative energy is a hypothetical form of energy that would have to repel rather than attract, allowing the space around the bubble to contract or expand in the desired manner. Although the warp drive remains speculative, recent advancements in quantum physics and experimental research have fueled interest in the concept. Some studies have proposed potential mechanisms for creating small amounts of negative energy, though the quantities required for a warp bubble are far beyond current capabilities. Nonetheless, the concept of manipulating space-time offers a glimpse into a future where interstellar travel might be possible, bypassing the limitations of conventional propulsion and relativistic speeds. The Alcubierre warp drive raises profound questions about the nature of space, time, and the limits of human exploration. If feasible, such a technology would enable humanity to reach distant star systems within a human lifetime, potentially opening up the galaxy for exploration and colonization. It invites us to consider a future where the boundaries of our solar system are no longer insurmountable and where new worlds lie within reach, redefining humanity's place in the cosmos. While the warp drive remains in the realm of theoretical physics, it serves as a reminder of the boundless potential of human imagination. Concepts like the Alcubierre warp drive encourage scientists to explore the limits of what is possible, pushing the boundaries of knowledge and inspiring future generations to pursue the dream of exploring the stars. Olbers paradox. Why is the night sky dark? Olbers paradox is a question that has intrigued astronomers and philosophers for centuries. If the universe is infinite, with an endless number of stars, why is the night sky dark? Named after German astronomer Heinrich Wilhelm Olbers, who popularized the question in the 19th century, the paradox challenges the notion of an eternal, static universe. In an infinite universe filled with stars, every line of sight should eventually meet the surface of a star, making the entire sky as bright as the sun. The resolution of Olbers' paradox lies in our understanding of the expanding universe and the finite age of the cosmos. The universe is not only expanding but also has a finite age around 13.8 billion years, which means we can only observe stars within a certain distance, known as the observable universe. Stars beyond this distance are invisible to us because their light has not had enough time to reach Earth. Another key factor is the finite lifespan of stars. Stars are not eternal, they are born, evolve, and eventually die, either fading into white dwarfs or exploding in supernovae. As a result, the number of stars in the observable universe is limited, and not all regions of space are illuminated by stars. Furthermore, as the universe expands, the wavelengths of light from distant galaxies stretch due to redshift, shifting their light into the infrared or even radio wavelengths, which are invisible to the human eye. The discovery of the cosmic microwave background, CMB, also plays a role in resolving Olbers' paradox. The CMB is the faint afterglow of the Big Bang, filling the universe with a background light that is now observed as microwaves. This radiation represents the surface of the observable universe at the time when it became transparent to light, around 380,000 years after the Big Bang. The CMB is faint and not visible to the naked eye, but it provides evidence that the universe was once filled with light and heat, gradually cooling over billions of years. Olbers' paradox highlights the dynamic nature of the universe and the role of cosmic expansion in shaping our observations. It serves as a reminder that the night sky is not simply empty, but is influenced by the universe's history, structure, and evolution. The dark sky is a testament to the finite age of the cosmos, the expansion of space, and the limitations of human perception, showing us that the universe is more complex than it appears. The quantum vacuum and virtual particles. The quantum vacuum, also known as the vacuum state, is the lowest possible energy state in quantum mechanics, where no particles exist in the traditional sense. However, even this empty space is not truly empty. Instead, it is filled with fleeting particles that pop into and out of existence, known as virtual particles. These virtual particles represent fluctuations in the quantum fields that permeate space, resulting in brief, spontaneous events that contribute to the vacuum energy. Virtual particles are a consequence of Heisenberg's uncertainty principle, which states that certain properties of a system, such as energy and time, cannot be precisely determined simultaneously. This principle allows for short-lived violations of energy conservation, giving rise to virtual particles that exist for fractions of a second before annihilating. Although they cannot be observed directly, virtual particles have measurable effects, such as the Casimir effect of force observed between two closely spaced plates in a vacuum, caused by the pressure exerted by virtual particles. The study of the quantum vacuum has led to profound discoveries about the nature of space, energy, and the fundamental forces. In particular, virtual particles play a role in mediating the forces between particles, such as the electromagnetic force between charged particles. In quantum electrodynamics, QAD, virtual pawns act as messenger particles that facilitate interactions between electrons and other charged particles. Similar mechanisms apply to the strong and weak nuclear forces, where virtual particles mediate interactions between quarks and other subatomic particles. Virtual particles also contribute to the energy density of the vacuum, which is believed to be linked to dark energy, the mysterious force driving the accelerated expansion of the universe. While the energy density predicted by quantum field theory is vastly higher than what is observed as dark energy, the link between vacuum fluctuations and cosmic expansion remains an area of intense research. The discrepancy between predicted and observed values, known as the cosmological constant problem, is one of the major unsolved mysteries in physics. The quantum vacuum challenges our understanding of emptiness, revealing that even the most empty regions of space are filled with fluctuations and interactions. Virtual particles highlight the dynamic nature of the quantum realm, where particles and forces arise from the fabric of space itself. The quantum vacuum serves as a reminder that the universe is a deeply interconnected system, where seemingly empty space holds the potential for creation, interaction, and the emergence of forces that shape the cosmos. Quantum entanglement, spooky action at a distance. Quantum entanglement is a phenomenon in which particles become interconnected in such a way that the state of one particle instantaneously affects the state of another, regardless of the distance between them. Described by Albert Einstein as spooky action at a distance, entanglement defies our classical understanding of locality and causality, suggesting that particles can remain linked across vast distances without any observable connection. Entanglement has profound implications for our understanding of reality and the fundamental nature of the quantum world. When two particles are entangled, measuring a property of one particle, such as its spin, will instantly determine the corresponding property of the other particle, even if they are separated by light years. This instantaneous connection seems to violate the speed limit set by the theory of relativity, as no information or influence should be able to travel faster than light. However, quantum entanglement does not involve the transmission of information in the conventional sense, which has led physicists to explore the deeper implications of this non-local effect. Quantum entanglement has been demonstrated in numerous experiments, including those with photons, electrons, and even larger molecules. One of the most famous experiments is known as the Bell test, which showed that measurements on entangled particles cannot be explained by any hidden variables that predetermine their outcomes. This result implies that entangled particles are fundamentally connected in a way that cannot be described by classical physics, pointing to the inherent weirdness of the quantum realm. Entanglement has also led to practical applications, such as quantum computing and quantum cryptography. In quantum computers, entangled particles, or qubits, can perform complex calculations much faster than classical bits, potentially revolutionizing fields such as cryptography, data analysis, and artificial intelligence. Quantum cryptography, on the other hand, uses entangled particles to create secure communication channels, as any attempt to intercept the entangled state would disrupt the system, alerting both parties to potential eavesdropping. In addition to technological applications, quantum entanglement raises philosophical questions about the nature of reality. Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that entanglement reflects a deeper level of connection between parallel universes, where each possible outcome of a quantum event exists in a separate reality. Other interpretations, like the pilot wave theory, propose that particles are guided by an underlying wave that exists beyond our perception, creating an invisible link between entangled particles. Quantum entanglement challenges our intuition about space, time, and causality, revealing a universe where connections can exist beyond the limitations of physical distance. It suggests that reality is far more interconnected than it appears, with particles and forces influencing each other in ways that transcend our classical understanding. Entanglement invites us to explore the mysteries of the quantum realm, where the boundaries between particles, space, and even time blur, revealing a universe woven together by hidden, unseen links. The observable universe and the expansion of space. The observable universe is the portion of the cosmos from which light has had time to reach us since the Big Bang, creating a horizon beyond which we cannot see. Due to the finite speed of light and the universe's age, about 13.8 billion years, the observable universe spans roughly 93 billion light-years in diameter. Beyond this limit lies the unobservable universe, potentially extending infinitely or containing regions vastly different from our own. The observable universe is expanding, meaning that galaxies are moving away from us, with those farther from Earth receding at higher velocities. This expansion, first discovered by Edwin Hubble in the 1920s, is driven by dark energy, a mysterious force that appears to counteract gravity on cosmic scales. As space itself expands, the distances between galaxies increase, causing light from distant objects to stretch into longer wavelengths, a phenomenon known as redshift. This redshift provides crucial information about the universe's structure, age, and rate of expansion. One of the most intriguing aspects of the observable universe is that its boundary is constantly shifting. As time progresses, light from previously unseen regions will eventually reach Earth, revealing new cosmic landscapes. However, due to the accelerating expansion of space, some galaxies will eventually recede beyond the observable limit, becoming permanently inaccessible to future observers. This phenomenon creates a dynamic horizon where the contents of the observable universe change over time as galaxies drift in and out of view. The expansion of the observable universe also raises questions about the nature of space and time. According to general relativity, the universe does not expand into anything. Rather, space itself is stretching, carrying galaxies with it. This expansion means that even the empty voids between galaxies are expanding, creating a universe where space is dynamic and evolving. This concept challenges our classical understanding of space as a static, unchanging backdrop, suggesting that space-time itself is an active participant in cosmic evolution. The observable universe is a reminder of the limits of human knowledge and the scale of the cosmos. It highlights the vastness of the universe, where billions of galaxies, each containing billions of stars, populate a region that is still only a fraction of the total universe. The expansion of space reveals the transient nature of observation, as galaxies and clusters shift in and out of reach, inviting us to ponder the infinite possibilities that lie beyond our cosmic horizon. The Casimir effect and the power of the quantum vacuum. The Casimir effect is a phenomenon that occurs when two uncharged, parallel metal plates are placed extremely close to each other in a vacuum. In this configuration, an attractive force arises between the plates, caused by the quantum fluctuations of the vacuum itself. Predicted by Dutch physicist Hendrik Casimir in 1948, the Casimir effect demonstrates that empty space is not truly empty but filled with virtual particles that create measurable forces. The Casimir effect arises from the quantum vacuum, where virtual particles constantly appear and annihilate, creating fluctuations in energy. When the plates are placed close together, the space between them restricts the wavelengths of these virtual particles, creating a lower energy density between the plates than in the surrounding vacuum. This difference in energy density generates a pressure that pushes the plates together, resulting in a measurable force that has been observed in laboratory experiments. The Casimir effect has profound implications for our understanding of the vacuum state and the nature of spacetime. It reveals that even in the absence of matter and radiation, the vacuum is filled with energy and fluctuations. This vacuum energy contributes to phenomena such as the Lamb shift in atomic energy levels and plays a role in fundamental forces. The Casimir effect demonstrates that the quantum vacuum is not a void but an active, dynamic field that influences particles and objects within it. The Casimir effect is also of interest for potential applications in nanotechnology and quantum mechanics. At very small scales, such as those encountered in microelectromechanical systems, MMS, the Casimir force becomes significant and can affect the behavior of tiny components. Understanding and controlling the Casimir effect could lead to advances in the design of microscopic devices, as well as new ways to harness quantum effects for practical applications. Additionally, the Casimir effect raises questions about the potential for vacuum energy as a source of power. While currently beyond our technological reach, some theorists speculate that it might be possible to tap into vacuum energy as a form of limitless energy. Such a breakthrough would revolutionize our understanding of energy and could lead to profound advancements in power generation, space travel, and technology. The Casimir effect serves as a reminder that even the emptiest regions of space are filled with invisible forces and energies. It challenges our classical understanding of nothingness, revealing a quantum realm where the vacuum is alive with fluctuations, interactions, and the potential for new forms of energy. The Casimir effect invites us to explore the hidden depths of space, where quantum effects shape the fabric of reality and offer glimpses into the universe's most fundamental properties. White dwarfs and the ultimate fate of stars. White dwarfs are the final evolutionary stage of low and medium mass stars, such as our Sun. After exhausting their nuclear fuel, these stars shed their outer layers in a process known as a planetary nebula, leaving behind a hot, dense core that slowly cools over billions of years. This core, known as a white dwarf, is an incredibly compact remnant with a mass comparable to that of the Sun but a volume similar to Earth. White dwarfs are composed primarily of electron-degenerate matter, where electrons are packed together so tightly that they exert a quantum pressure, known as electron degeneracy pressure, which prevents the star from collapsing further. This pressure, a consequence of the Pauli exclusion principle, allows white dwarfs to remain stable despite their lack of nuclear fusion. Over time, they gradually radiate away their residual heat, eventually cooling to become black dwarfs, hypothetical, fully cooled remnants that do not emit any light. The formation of a white dwarf marks the end of a star's life cycle, but white dwarfs can still play active roles in the cosmos. In binary systems, where a white dwarf orbits a companion star, the white dwarf can pull matter from its companion, forming an accretion disk. If enough material accumulates, the white dwarf can reach a critical mass known as the Chandrasekhar limit, around 1.4 times the mass of the Sun. At this point, it may undergo a thermonuclear explosion, resulting in a type Ioa supernova, a powerful explosion that releases a vast amount of energy and disperses elements into space. Type Ioa supernova are valuable tools in cosmology because they have consistent peak luminosities, allowing astronomers to use them as standard candles to measure cosmic distances. Observations of distant Type Ia supernovae provided the first evidence for the accelerating expansion of the universe, leading to the discovery of dark energy. White dwarfs, therefore, play a crucial role in understanding the large-scale structure and evolution of the cosmos. White dwarfs also offer insights into the ultimate fate of stars and the chemical evolution of galaxies. As stars evolve and die, they release elements such as carbon, oxygen, and nitrogen into space, enriching the interstellar medium and contributing to the formation of new stars and planets. This cycle of stellar death and rebirth is fundamental to the evolution of galaxies and the development of complex structures, including the building blocks of life. White dwarfs are silent witnesses to the life cycles of stars and the processes that shape galaxies. They remind us that even the quietest objects in the universe can have far-reaching effects, contributing to the enrichment of the cosmos and the expansion of our understanding. By studying white dwarfs, we gain a glimpse into the future of our sun and the legacy of stars as they transition from vibrant spheres of fusion to quiet, enduring remnants. Neutron stars, cosmic heavyweights. Neutron stars are the incredibly dense remnants of massive stars that have exploded in supernovae. When a star between about 8 and 20 times the mass of the Sun exhausts its nuclear fuel, it undergoes a gravitational collapse, forcing protons and electrons to combine and form neutrons. This process results in a neutron star, a compact object with a mass greater than the Sun, but only about 10 kilometers in diameter, meaning that a teaspoon of neutron star material would weigh billions of tons. The extreme density of neutron stars creates gravitational and magnetic fields that are among the most powerful in the universe. Their gravitational pull is so intense that light bends around them, allowing astronomers to observe the backside of a neutron star from certain angles. Neutron stars rotate at incredibly high speeds, with some spinning hundreds of times per second. These rapidly rotating neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses. The magnetic fields of neutron stars can reach up to 1 trillion times stronger than Earth's, creating conditions where ordinary atomic structures cannot exist. Electrons are forced to spiral around magnetic field lines, and the surface of the star is thought to be covered in a crust of iron atoms tightly compressed into a lattice structure. Beneath the crust lies a sea of neutrons, which may become a neutron superfluid due to the extreme pressure, allowing them to flow without friction. In addition to their magnetic fields, neutron stars can exhibit dramatic phenomena such as star quakes. These quakes occur when the crust of the neutron star undergoes shifts, releasing sudden bursts of energy. In magnetars, a type of neutron star with an exceptionally strong magnetic field, these star quakes can result in intense gamma-ray flares, among the most energetic events in the Milky Way. Neutron stars are critical to our understanding of extreme states of matter. They exist at the edge of what we know about nuclear physics, with pressures and densities that cannot be replicated in any laboratory on Earth. Studying neutron stars allows physicists to explore how matter behaves under the most extreme conditions, providing insights into the fundamental properties of particles and forces. Neutron stars remind us of the relentless power of gravity and the strange, exotic forms matter can take under extreme conditions. They stand as cosmic heavyweights, bearing the legacy of massive stars that once lit up the galaxy. Through the study of neutron stars, we gain a window into the mysterious realms of ultra-dense matter, revealing the hidden extremes of our universe. Cosmic inflation, the universe's rapid birth. Cosmic inflation is a theory that describes a period of extremely rapid expansion in the early universe, occurring just fractions of a second after the Big Bang. According to this theory, the universe expanded exponentially, doubling in size many times over in less than 1/1,000,000th of a second. This sudden burst of expansion smoothed out any irregularities and distributed matter evenly, creating the homogeneous, isotropic universe we observe today. The concept of inflation was proposed by physicist Alan Guth in the 1980s to address several puzzles in cosmology, such as the horizon problem and the flatness problem. The horizon problem arises because regions of the universe that are far apart appear to have the same temperature and density, despite not having had enough time to interact with each other according to the speed of light. Inflation solves this by suggesting that these regions were once close together before inflation expanded them beyond each other's reach. Inflation also addresses the flatness problem, which concerns the universe's geometry. Observations suggest that the universe is remarkably flat, meaning that space is not curved on large scales. For this to be the case, the initial conditions of the universe had to be incredibly precise. Inflation explains this by stretching any initial curvature, making the universe appear flat on the scales we observe. The inflationary period is thought to have left imprints in the cosmic microwave background, CMB, the faint glow left over from the Big Bang. Tiny fluctuations in temperature within the CMB correspond to fluctuations that were stretched to cosmic scales during inflation. These fluctuations later became the seeds of galaxies, clusters, and superclusters as gravity amplified them, leading to the cosmic structures we see today. One of the goals of cosmology is to detect primordial gravitational waves, ripples in space-time produced by inflation. These gravitational waves would have left subtle patterns in the CMB, providing evidence of inflation's occurrence. While these signals are incredibly faint, upcoming experiments in observatories may soon be able to detect them, offering a direct glimpse into the universe's earliest moments. Cosmic inflation reshapes our understanding of the Big Bang and the universe's beginning, suggesting that the cosmos emerged not from a single explosion, but from an era of rapid, exponential expansion. It challenges our perception of time, space, and scale, showing that even the smallest fluctuations can shape the largest structures in existence. Through inflation, we glimpse the birth of the universe as a dynamic, ever-expanding realm filled with boundless potential. The faint young sun paradox, early Earth's climate mystery. The faint young sun paradox refers to a puzzling inconsistency between early Earth's climate and the sun's estimated brightness at that time. According to stellar evolution models, the sun was about 30% dimmer when Earth formed over 4 billion years ago. With a weaker sun, Earth should have been a frozen planet, incapable of supporting liquid water or life. However, geological evidence shows that early Earth had liquid oceans and a relatively warm climate, suggesting that something kept the planet from freezing. One proposed solution to this paradox involves greenhouse gases, such as carbon dioxide and methane, which could have trapped more heat in Earth's atmosphere, compensating for the sun's lower output. Higher levels of volcanic activity and tectonic shifts in early Earth could have released these gases, creating a thicker, warmer atmosphere. Methane, in particular, is an extremely potent greenhouse gas and could have contributed significantly to early Earth's warmth if present in high concentrations. Another possibility is that the young sun was more active and emitted more ultraviolet radiation, which would have interacted with Earth's atmosphere, potentially producing greenhouse gases and warming the planet. This hypothesis aligns with evidence of higher solar activity in young stars, which tend to emit more radiation early in their life cycles before stabilizing. If early Earth's atmosphere could absorb this energy, it might explain the warmer climate despite a fainter sun. Some scientists have explored the idea of geological or biological processes contributing to the warming. Primitive life forms, such as early cyanobacteria, could have influenced atmospheric composition by producing methane as a byproduct. The development of microbial life in Earth's early oceans may have played a role in maintaining a stable climate, creating a self-sustaining biological thermostat that regulated atmospheric gases. The faint young sun paradox invites us to explore the delicate balance of factors that make Earth habitable. It reminds us that Earth's climate and atmosphere are products of complex interactions between geology, biology, and solar activity. This paradox highlights the resilience and adaptability of our planet's early environment, showing that life can emerge and thrive even under challenging conditions. Understanding the faint young sun paradox not only sheds light on Earth's history, but also has implications for the search for habitable planets. It suggests that planets orbiting fainter stars could potentially support life if they have the right atmospheric conditions. This insight broadens the scope of habitability beyond stars similar to our Sun, expanding the possibilities for finding life in the universe. The Great Attractor, a cosmic mystery. The Great Attractor is a gravitational anomaly located in the direction of the Centaurus and Hydra constellations, about 150 to 250 million light-years from Earth. It appears to be drawing our galaxy, the Milky Way, along with thousands of other galaxies, toward it at a speed of roughly 600 kilometers per second. This powerful pull suggests the presence of a massive concentration of matter, yet much of this region is obscured by the zone of avoidance, an area of the sky hidden by our galaxy's dense gas and dust. The Great Attractor's gravitational influence is so strong that it affects not only the Milky Way but also the entire Laniakea supercluster, a collection of galaxies stretching over 500 million light-years. This supercluster is itself moving toward the Great Attractor, drawn by its mysterious gravitational pull. However, the exact nature of the Great Attractor remains uncertain, as it is shrouded in cosmic dust and remains challenging to study directly. One hypothesis is that the Great Attractor is a massive supercluster or concentration of dark matter, creating a gravitational well that attracts surrounding galaxies. Observations of galaxy movement suggest that dark matter may be concentrated in this region, though its exact distribution is difficult to map. The Great Attractor could also be part of an even larger structure, such as the Shapley supercluster, which lies beyond it and exerts additional gravitational influence on surrounding galaxies. The study of the Great Attractor has led astronomers to propose that it may be part of the cosmic web, a network of dark matter filaments connecting galaxies and clusters across vast distances. These filaments create rivers of galaxies, guiding their movement toward areas of high density. The Great Attractor could be a dense node within this web, where dark matter and ordinary matter converge, shaping the structure of the universe. The Great Attractor serves as a reminder of the mysteries that lie beyond our view, suggesting that the universe contains massive structures that continue to influence galaxies on scales beyond human comprehension. It challenges our understanding of cosmic organization, hinting at a universe where vast, unseen forces govern the movement of galaxies, clusters, and superclusters across billions of light-years. The Great Attractor invites us to consider the hidden influences that shape the cosmos, expanding our understanding of the universe's large-scale structure. Through the study of this gravitational anomaly, we learn that the universe is a dynamic, interconnected system, filled with forces and structures that remain hidden from direct observation. The Great Attractor reminds us that even the most distant galaxies are part of a vast cosmic flow, guided by gravitational currents that span the universe. The shadow of a black hole, a groundbreaking observation. In April 2019, humanity captured the first image of a black hole, marking a monumental achievement in astrophysics. The black hole, located in the center of the galaxy M87, lies 55 million light-years from Earth and has a mass 6.5 billion of the Sun. The image, produced by the Event Horizon Telescope, EAT collaboration, shows a bright ring of light encircling a dark shadow, the event horizon beyond which nothing can escape the black hole's gravitational pull. The EAT is a network of radio telescopes across the globe, synchronized to act as a single, Earth-sized telescope. By observing the black hole in M87 with unprecedented resolution, scientists were able to capture light bending around the event horizon, creating the characteristic shadow of the black hole. This groundbreaking image provided visual confirmation of Einstein's predictions about black holes and offered a glimpse into one of the universe's most extreme environments. The shadow of a black hole forms because of its immense gravitational pull, which warps space-time so intensely that light is bent around it. The bright ring seen in the image is composed of superheated gas and plasma swirling around the black hole at nearly the speed of light. The gas emits light as it accelerates and heats up, creating a glowing ring. The center of the ring appears dark because any light that crosses the event horizon is absorbed, creating a silhouette. This first image of a black hole has profound implications for our understanding of gravity, space-time, and the fundamental laws of the universe. By studying the shape and structure of the black hole's shadow, scientists can test the predictions of general relativity in a region where gravity is exceptionally strong. Future observations may reveal subtle deviations from Einstein's equations, potentially pointing to new physics or insights into quantum gravity. The EAT continues to observe other black holes, including Sagittarius A, the supermassive black hole at the center of our Milky Way. Each new image and observation advances our understanding of these enigmatic objects, bringing us closer to unraveling the mysteries of black holes and the forces that govern them. The shadow of a black hole is a testament to human ingenuity and a reminder that even the darkest realms of the universe can be explored through the lens of science. This observation marks a new era in astronomy, where black holes can be studied not just through indirect effects, but directly, through images that capture their shadows against the glowing fabric of the cosmos. It shows that the boundaries of human knowledge are constantly expanding as we push deeper into the unknown and illuminate the darkest corners of existence. A legacy of light and magnetism. Pulsars and magnetars are not only remnants of stellar death, but also cosmic beacons and laboratories that illuminate the darkest corners of the universe. Their extreme properties challenge our understanding of physics, offering clues about the nature of matter, energy, and the fundamental forces that shape reality. By studying these enigmatic objects, we gain a deeper appreciation for the interconnected processes that govern the cosmos, from the birth of stars to the creation of heavy elements and the ripples of space-time itself. Pulsars and magnetars remind us that even in the aftermath of destruction, the universe continues to create, inspire, and reveal its secrets. The interstellar medium, the universe's invisible matter. The interstellar medium, ISM, is the vast expanse of gas, dust, and cosmic radiation that exists between the stars and a galaxy. Though it appears empty to the naked eye, the ISM is teeming with activity, serving as the birthplace of stars, the repository of stellar remnants, and the highway for cosmic phenomena. This diffuse medium plays a crucial role in the life cycle of galaxies, connecting the processes of star formation, stellar evolution, and cosmic enrichment. The components of the interstellar medium. The ISM is composed primarily of hydrogen and helium, with trace amounts of heavier elements and dust. These components exist in various phases, determined by temperature and density. Molecular clouds, the coldest and densest regions of the ISM. Molecular clouds are the birthplaces of stars and planets. Temperatures within these clouds can drop to just a few degrees above absolute zero, allowing hydrogen molecules, H2, to form. These clouds, like the famous Orion molecular cloud, harbor the raw materials for star formation and often contain complex organic molecules. Neutral atomic gas. This phase consists of hydrogen atoms, H, in regions with moderate temperatures, 110,000 K. Neutral hydrogen is detected through its characteristic 21 centimeter emission line, a key tool for mapping the structure of galaxies. Ionized gas, found in regions near hot, young stars. Ionized gas, H, emits visible and ultraviolet light. These regions, called HII regions, are glowing clouds of ionized hydrogen, such as the iconic Eagle Nebula's pillars of creation. Interstellar dust. Though it constitutes only about 1% of the ISM's mass, dust plays a critical role in star formation and chemistry. Dust grains, composed of silicates, carbon and ice, shield molecular clouds from ultraviolet radiation, allowing complex molecules to form. Dust also scatters and absorbs light, giving nebulae their distinct colors and obscuring distant stars. Cosmic rays, high-energy particles, primarily protons, traverse the ISM at nearly the speed of light. These cosmic rays originate from supernovae and active galactic nuclei, influencing the chemistry and ionization of the ISM. Star formation in the interstellar medium. The ISM is a dynamic environment shaped by the interplay of gravity, pressure, and turbulence. Star formation begins when molecular clouds collapse under their own gravity, forming dense cores that become protostars. However, the process is far from straightforward. Magnetic fields, turbulence, and feedback from nearby stars can slow or halt collapse, making star formation an inefficient process. Regions of active star formation, such as the Carina Nebula, showcase the complexity of these interactions. Massive stars within these regions emit powerful stellar winds and radiation, carving out cavities in the ISM and triggering the formation of new stars in nearby gas clouds. This feedback mechanism ensures that star formation occurs in cycles, spreading across the galaxy over millions of years. The role of supernovae in the ISM. Supernovae are critical to the evolution of the ISM, injecting energy, enriching it with heavy elements, and driving its dynamic behavior. When a massive star explodes, it ejects vast quantities of material into the ISM, creating a shockwave that compresses surrounding gas. This compression can trigger new star formation, continuing the cycle of stellar birth and death. Supernova remnants, such as the Crab Nebula, are key sites for studying the interaction between supernovae and the ISM. These remnants reveal how energy and material are redistributed, shaping the structure of the ISM on both small and large scales. Interstellar turbulence and magnetic fields. The ISM is far from uniform. It is a turbulent environment where regions of different densities and temperatures coexist. Turbulence plays a key role in regulating star formation, as it creates density fluctuations that can initiate or inhibit gravitational collapse. Magnetic fields thread through the ISM, influencing its dynamics and structure. These fields, though weak compared to those on Earth, are strong enough to shape the motion of gas and dust, guiding the formation of molecular clouds and regulating the efficiency of star formation. Observations of polarized light from dust grains provide insights into the orientation and strength of these magnetic fields. Galactic winds and the ISM.
The ISM is not confined to individual galaxies. It interacts with the intergalactic medium, IGMA, through processes like galactic winds. These winds, driven by supernovae and active galactic nuclei, expel gas and dust into intergalactic space, enriching the IGMA with heavy elements. Galactic winds play a critical role in galaxy evolution, regulating star formation and redistributing material across cosmic scales.
The ISM is a chemical factory. The ISM is a hub of chemical activity where molecules form, interact, and evolve. Dense molecular clouds harbor complex organic molecules, including precursors to amino acids and other building blocks of life. These molecules are protected from harsh radiation by dust grains, which serve as surfaces for chemical reactions. The detection of molecules like water, methanol, and formaldehyde in the ISM highlights its role in the chemistry of the universe. Observations of protoplanetary disks, where planets form, suggest that the chemistry of the ISM influences the composition of planetary systems, potentially delivering the ingredients for life to young planets. The ISM and the Milky Way. In our own Milky Way, the ISM is distributed unevenly, concentrated in the spiral arms and central regions of the galaxy. Observations with telescopes like ALMA, Atacama Large Millimeter Array, and SOFIA, Stratospheric Observatory for Infrared Astronomy, have revealed the intricate structure of the ISM, from massive molecular clouds to diffuse regions of ionized gas. The study of the ISM provides insights into the Milky Way's history and future. By mapping the distribution and motion of gas and dust, astronomers can trace the processes that shape the galaxy, from the formation of spiral arms to the influence of the central supermassive black hole. The future of ISM research. Advances in technology are revolutionizing our understanding of the ISM. Instruments like the James Webb Space Telescope, JWST, are providing unprecedented views of molecular clouds and star-forming regions, revealing the interplay of physics and chemistry in exquisite detail. Future missions, such as the Square Kilometre Array (SKA), will map the distribution of hydrogen across the universe, uncovering the structure of the ISM in distant galaxies. The interstellar medium, though seemingly empty, is a vital component of the cosmos. It connects the life cycles of stars, the evolution of galaxies, and the chemistry of life. By studying the ISM, we uncover the hidden processes that shape the universe, gaining a deeper appreciation for the complexity and interconnectedness of the cosmos. The life cycle of galaxies: formation, evolution, and transformation. Galaxies are the grand architects of the cosmos, vast collections of stars, gas, dust, and dark matter that evolve over billions of years. From their humble beginnings as small protogalaxies to their majestic forms as spiral, elliptical, or irregular galaxies, their life cycle is shaped by cosmic forces and intricate processes. Understanding the life cycle of galaxies not only reveals the history of the universe, but also illuminates the forces that continue to shape it. The formation of galaxies. The story of galaxies begins in the early universe, a few 100 million years after the Big Bang. During this period, known as the Cosmic Dark Ages, the universe was filled with a nearly uniform distribution of hydrogen and helium gas. Tiny density fluctuations, imprinted during cosmic inflation, served as seeds for galaxy formation. Dark matter played a critical role in this process. Though invisible, it exerted gravitational influence, pulling gas into regions of higher density. These regions collapsed to form the first protogalaxies, small and irregular clumps of stars and gas. Over time, these protogalaxies merged and accreted material, growing into the massive galaxies we see today. The first stars within these galaxies, known as population II stars, were massive and short-lived. Their supernova explosions enriched the surrounding gas with heavy elements, allowing for the formation of more complex molecules and the birth of new generations of stars. Galaxy classification: spirals, ellipticals, and irregulars. Galaxies are classified into three main types based on their structure. Spiral galaxies, characterized by a central bulge surrounded by flat, rotating disks of stars and gas. Spiral galaxies often have distinct arms where star formation is active. The Milky Way and Andromeda are prime examples. These galaxies are rich in gas and dust, fueling ongoing star formation. Elliptical galaxies: these galaxies have a more spherical or elongated shape and lack the defined structure of spirals. They contain older, redder stars and have little gas or dust, indicating that star formation has largely ceased. Elliptical galaxies often form through the mergers of smaller galaxies. Irregular galaxies, lacking a distinct shape. Irregular galaxies are often the result of gravitational interactions or collisions. These galaxies are rich in gas and dust, making them active sites of star formation. Galaxy evolution: growth and interaction. Galaxies evolve through a combination of internal processes and external influences. Internally, star formation, supernovae, and black hole activity shape their structure and composition. Externally, interactions with other galaxies and the intergalactic medium drive significant changes. Mergers and collisions: galaxy mergers are among the most transformative events in their evolution. When two galaxies collide, their stars pass through each other, but their gas and dust interact, triggering bursts of star formation. Over time, the merging galaxies may settle into a new, larger structure, often becoming elliptical galaxies. The Milky Way's future merger with Andromeda will likely result in a new galaxy, sometimes referred to as Milkomeda. Observations of colliding galaxies, such as the Antennae galaxies, provide a glimpse into the dynamic processes at play. Galactic cannibalism: larger galaxies often grow by consuming smaller ones in a process called galactic cannibalism. The gravitational pull of the larger galaxy disrupts and absorbs the smaller galaxy, adding its stars, gas, and dark matter to the larger system. This process contributes to the growth of massive elliptical galaxies. Starburst galaxies: in some cases, interactions or internal processes lead to periods of intense star formation, creating starburst galaxies. These galaxies burn through their gas rapidly, producing large numbers of new stars over a relatively short period. The role of supermassive black holes in galaxy evolution. At the center of nearly every massive galaxy lies a supermassive black hole, whose mass is often millions or billions of times that of the Sun. These black holes influence their host galaxies through feedback processes, such as jets of high-energy particles and radiation emitted during active phases. When a supermassive black hole accretes matter, it powers an active galactic nucleus, AGN, emitting enormous amounts of energy. This energy can heat or expel gas, regulating star formation and shaping the galaxy's evolution. The relationship between a galaxy's central black hole and its properties, such as the M-sigma relation, highlights the interconnected growth of galaxies and their black holes. Galactic quenching: the end of star formation. Galaxies do not form stars indefinitely. Over time, processes such as feedback from black holes, supernovae, and the depletion of gas reservoirs can halt star formation, transforming galaxies into quiescent systems. This transition, known as quenching, marks a significant phase in a galaxy's life cycle. Quenching can be triggered by feedback processes. Energy from AGNs and supernovae can heat or expel gas, preventing it from cooling and forming new stars. Galaxy mergers: the chaotic interactions during mergers can disrupt gas reservoirs, shutting down star formation. Environmental effects: galaxies in dense clusters experience ram pressure stripping, where their gas is removed by the surrounding intergalactic medium, leading to quenching. Quiescent galaxies, often elliptical in shape, continue to evolve slowly, their stars aging and cooling over billions of years. the intergalactic medium and galactic recycling. The intergalactic medium, IGM, the diffuse gas between galaxies, plays a vital role in their life cycle. Galaxies accrete gas from the IGM to fuel star formation, while feedback processes return enriched material to the IGM, creating a cycle of matter and energy exchange.
This galactic recycling enriches the universe with heavy elements, spreading the building blocks of stars, planets, and life. Observations of the IGM using telescopes like the James Webb Space Telescope, JWST, are revealing the complex interactions between galaxies and their environments.
The future of galaxies. As the universe continues to expand, galaxies will evolve in new and fascinating ways. Over billions of years, the accelerating expansion driven by dark energy will isolate galaxies from one another, as the space between them grows faster than the speed of light. In this distant future, galaxies like the Milky Way will become island universes, isolated in the vast emptiness of space. Internally, galaxies will slowly fade as star formation ceases and existing stars burn out. White dwarfs will cool into black dwarfs, and black holes will dominate the remnants of galactic cores. The ultimate fate of galaxies depends on the nature of dark energy and the universe's long-term evolution, whether through a big freeze, big rip, or other scenarios. Galaxies, the dynamic engines of the universe. Galaxies are more than collections of stars and matter. They are dynamic engines that drive the evolution of the universe. Their interactions, growth, and transformations reflect the forces that shape the cosmos, from gravity and dark matter to black holes and interstellar chemistry.
By studying galaxies, we unravel the history of the universe, exploring its past, present, and future. From their brilliant clusters of stars to their hidden dark matter halos, galaxies remind us of the intricate and interconnected processes that govern the cosmos, offering a window into the vast and ever-changing universe.
The intergalactic medium, the universe's vast and mysterious expanse. Between the luminous beacons of galaxies lies the intergalactic medium, IGM, a vast and tenuous expanse of gas, plasma, and dark matter. While it may seem empty, the IGM is a critical component of the cosmos, serving as the connective tissue of the universe and a key player in its evolution. This medium provides a bridge between galaxies, influencing their growth, interactions, and the large-scale structure of the universe. The composition of the intergalactic medium. The IGM consists primarily of hydrogen and helium, the two lightest and most abundant elements, formed in the first few minutes after the Big Bang during primordial nucleosynthesis. Trace amounts of heavier elements, known as metals in astrophysical terms, are also present, enriched by supernovae and galactic winds.
The IGM exists in different states, depending on its temperature and density.
The warm-hot intergalactic medium, WIM. This phase is composed of gas at temperatures ranging from 10,000 to 10 million Kelvin. It is thought to contain a significant fraction of the universe's baryonic matter, much of which remains hidden in observations due to its diffuse nature. Ionized gas, most of the IGM is ionized, meaning its hydrogen and helium atoms have been stripped of electrons. This ionization occurred during two key epochs. Rhyonisation, about 500 million years after the Big Bang. The first stars and galaxies emitted tense ultraviolet radiation, reionizing the neutral hydrogen left over from recombination. Helium reionization. Occurring later, this process was driven by the energetic radiation from quasars, reionizing helium and heating the IGM further.
Lyman alpha forest. The IGM's neutral hydrogen is detectable through absorption lines in the spectra of distant quasars. These lines, known as the Lyman alpha forest, provide a detailed map of the IGM's distribution, temperature, and composition.
The IGM's role in cosmic structure formation. The IGM is a vital component of the cosmic web, the large-scale structure of the universe. Gravity pulls the gas into filaments that connect galaxies and clusters, creating a network of interconnected structures spanning hundreds of millions of light years. Observations and simulations show that the IGM traces the distribution of dark matter, which serves as the scaffolding for this cosmic web. As galaxies form and grow, they accrete gas from the IGM along these filaments. This infall of material fuels star formation and contributes to the growth of supermassive black holes. The interplay between galaxies and the IGM ensures the continuous recycling of matter and energy, maintaining the dynamism of the universe.
Galactic feedback in the IGMA.
Galaxies influence the IGMA through feedback processes driven by supernovae, stellar winds, and active galactic nuclei (AGN). These processes inject energy and metals into the surrounding medium, enriching the IGMA and affecting its thermal state. For example,
Supernova feedback. The explosion of massive stars releases shockwaves that heat and expel gas from galaxies. This gas mixes with the IGM, spreading heavy elements like carbon, oxygen, and iron.
AGN feedback. Jets and outflows from supermassive black holes can heat the IGMA, preventing gas from cooling and falling back into galaxies. This process regulates star formation and shapes the large-scale distribution of gas. The enrichment of the IGM with metals provides valuable information about the history of star formation and galactic evolution. Observations of the IGM's metallicity using X-ray and ultraviolet telescopes reveal the cumulative effects of billions of years of feedback. The missing baryon problem and the IGM. For decades, astronomers faced the missing baryon problem, where the observed amount of ordinary matter in the universe fell short of theoretical predictions. The solution to this mystery lies in the IGMA, specifically the WIM. Observations of the WIM through X-ray emissions and absorption lines in quasar spectra have accounted for the missing baryons, confirming that much of the universe's ordinary matter resides in this diffuse medium. The study of the WIM is challenging due to its faint signals, but advances in telescope technology, such as the Chandra X-ray Observatory and the upcoming Athena mission, are providing increasingly detailed insights into this elusive component of the universe. The IGM and the epoch of reionization.
The IGM played a central role during the epoch of reionization, a transformative period when the first stars and galaxies ionized the universe's neutral hydrogen. This era marked the end of the cosmic dark ages and the beginning of visible structures in the universe.
Observations of reionization are made possible by studying the CMB, the Lyman alpha forest, and high redshift galaxies. These data reveal the timeline of reionization and the sources of the ultraviolet radiation responsible for it. Understanding this epoch sheds light on the formation of the first galaxies and the early evolution of the IGMA. Intergalactic medium as a laboratory for fundamental physics. The IGMA is an ideal environment for testing theories of fundamental physics. Its diffuse nature and vast scales provide a unique laboratory for studying dark matter. The IGMA traces the distribution of dark matter, offering indirect evidence of its presence and properties. Simulations of the cosmic web, based on dark matter dynamics, align closely with observations of the IGMA. Cosmic magnetism. The magnetic fields threading the IGMA are poorly understood but could offer insights into their origin, evolution, and impact on galaxy formation. Neutrinos and cosmic rays. High-energy particles from cosmic sources propagate through the IGMA, providing information about their origins and interactions with the medium. Future studies of the intergalactic medium. The next generation of observatories promises to revolutionize our understanding of the IGMA. Instruments like the James Webb Space Telescope, JWST, and the European Space Agency's Euclid mission are exploring the IGM's role in cosmic structure formation and evolution. At the same time, X-ray and radio telescopes are probing the WIM and its interactions with galaxies. Simulations of the IGMA using supercomputers and advanced algorithms are also advancing our knowledge. These simulations recreate the formation and evolution of the cosmic web, helping scientists interpret observations and refine models of the universe's growth.
The IGMA, the universe's vast interconnection.
The intergalactic medium is more than the space between galaxies, it is the fabric that connects them, driving the processes that shape the cosmos. By studying the IGMA, we uncover the hidden dynamics of the universe, from its earliest moments to its current structure. Through its interplay with galaxies, the IGMA ensures the continuous cycle of matter and energy, enriching the cosmos and enabling the formation of stars, planets, and life. It is a reminder that even the seemingly empty regions of space are filled with activity, contributing to the grand tapestry of the universe. Cosmic inflation, the universe's explosive beginning. Cosmic inflation is one of the most groundbreaking concepts in modern cosmology, offering a solution to many of the mysteries surrounding the early universe. This rapid and exponential expansion, theorized to have occurred within the first fraction of a second after the Big Bang, provides a framework for understanding the universe's uniformity, structure, and vastness. Although it lasted for an almost unimaginably short time, its effects have shaped the cosmos as we observe it today. The origins of inflation theory. The theory of inflation was first proposed in the early 1980s by physicist Alan Guth as a modification to the standard Big Bang model. The Big Bang theory explained the universe's expansion and the formation of elements but left several key questions unanswered. The Horizon Problem, observations of the cosmic microwave background, CMB, reveal that the universe is remarkably uniform in temperature across vast distances. However, regions of the CMB are so far apart that they could not have exchanged information or energy under standard Big Bang conditions. The flatness problem. The observable universe appears to be spatially flat, meaning that its geometry is neither curved nor open. Achieving such a balance requires finely tuned initial conditions, which seemed implausible. The monopole problem. Grand unified theories, GUTs, predicted the existence of magnetic monopoles, hypothetical particles with a single magnetic pole. However, these have never been observed, suggesting something suppressed their production or abundance. Inflation addressed these problems by positing that the universe underwent a brief but extreme expansion, growing exponentially in size. This expansion stretched and smoothed out any initial irregularities, creating the uniform and flat cosmos we see today, while diluting unwanted relics like monopoles. How inflation worked. Inflation is thought to have been driven by a scalar field, often called the inflaton field. This field had a high potential energy density, which acted like a repulsive force, causing space itself to expand exponentially. During this phase, the universe doubled in size repeatedly, expanding by a factor of at least 102, 61026 1026 in less than 103, 21032 1032 seconds. Eventually, the inflaton field transitioned to a lower energy state, releasing its stored energy in a process known as reheating. This energy was converted into particles and radiation, kickstarting the standard Big Bang phase and setting the stage for the universe's continued evolution. The imprints of inflation. Inflation left observable imprints on the universe that provide strong evidence for its occurrence. Cosmic microwave background, CMB. The CMB is a snapshot of the universe when it was just 380,000 years old. Tiny fluctuations in its temperature correspond to variations in density, seeded by quantum fluctuations during inflation. These variations later grew into the large-scale structures of galaxies and clusters. Large-scale structure. The distribution of galaxies and galaxy clusters aligns with the patterns predicted by inflation. These structures form a cosmic web that reflects the amplified quantum fluctuations stretched during the inflationary epoch. Primordial gravitational waves. Inflation would have generated ripples in space-time, known as primordial gravitational waves. While these waves have not yet been directly detected, they may be observable as subtle polarization patterns in the CMB. The quantum origins of structure. One of inflation's most remarkable implications is that the universe's large-scale structure originated from quantum fluctuations. During inflation, these fluctuations in the inflaton field were stretched to macroscopic scales, creating regions of slightly different densities. These differences acted as the seeds for the formation of stars, galaxies, and clusters. The idea that quantum mechanics, a theory governing the microscopic world, could influence the structure of the entire cosmos highlights the deep interconnectedness of physics across scales. Variants and extensions of inflation. While the basic idea of inflation is widely accepted, many variants and extensions have been proposed, each offering different mechanisms or implications. Chaotic inflation. This model suggests that inflation began in a chaotic state, with the inflaton field taking on random values across the universe. Eternal inflation. In this scenario, inflation never completely ends in certain regions of the universe. Instead, pockets of space transition out of the inflationary phase, creating bubble universes that could form a multiverse. Hybrid inflation. This model involves multiple fields interacting to drive inflation and end it, offering a richer framework for exploring the dynamics of the early universe. Each of these models provides a different perspective on the nature of inflation and its potential connections to other areas of physics, such as string theory and quantum gravity. Challenges and open questions. Despite its successes, inflation is not without challenges. The inflaton field. While inflation requires a scalar field, the exact nature of the inflaton remains unknown. Determining its properties and origin is a major focus of theoretical physics. Initial conditions. Inflation assumes certain initial conditions, such as a pre-existing universe. Understanding why these conditions existed is a profound question.
Fine-tuning. Some parameters in inflation models require fine-tuning, leading to debates about whether inflation is the most natural explanation.
Ongoing research, including experiments designed to detect primordial gravitational waves and refine measurements of the CMB, aims to address these questions and test the predictions of inflationary models. Inflation's role in cosmic evolution. Inflation is more than just a phase of rapid expansion. It is the foundation of our understanding of the universe's earliest moments. By smoothing out irregularities, seeding structure, and explaining the universe's flatness and uniformity, inflation provides a coherent framework for the cosmos we observe. Moreover, inflation connects cosmology with fundamental physics, bridging the macroscopic and quantum realms. It offers clues about the unification of forces, the nature of space-time, and the origins of the universe itself. The legacy of inflation. Cosmic inflation represents one of the most profound shifts in our understanding of the universe. It explains how the cosmos transitioned from a quantum state to the vast and structured expanse we see today. Its predictions have been confirmed by decades of observations, yet its mysteries continue to inspire exploration. As new technologies and theories emerge, the study of inflation will remain at the forefront of cosmology, revealing the secrets of the universe's beginning and its potential futures. Inflation reminds us that even the briefest moments in cosmic history can have lasting and transformative effects, shaping the universe on the grandest scales. Dark matter. The universe's hidden framework. Dark matter is one of the most mysterious and vital components of the universe, comprising about 27% of its total mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Yet its presence is undeniable, inferred through its gravitational effects on galaxies, clusters, and the large-scale structure of the cosmos. Understanding dark matter is a central challenge in modern physics and cosmology, promising to unlock the secrets of the universe's composition and evolution. The evidence for dark matter.
The existence of dark matter was first proposed in the early 20th century to explain discrepancies between the observed and expected behavior of galaxies and clusters. Key pieces of evidence include
galaxy rotation curves. Observations of spiral galaxies reveal that their outer regions rotate at much higher speeds than expected based on visible matter alone. This suggests the presence of an unseen mass providing additional gravitational pull. Galaxy clusters. In the 1930s, Fritz Zwicky studied the Coma cluster and found that its galaxies were moving too quickly to be held together by their visible mass. He coined the term dark matter to describe the missing mass needed to explain this phenomenon.
Gravitational lensing, the bending of light by massive objects, as predicted by Einstein's general relativity, provides a direct measure of mass distribution. Studies of galaxy clusters show that their total mass far exceeds what can be accounted for by visible matter alone.
Cosmic microwave background, CMB. The patterns in the CMB, a relic of the early universe, are shaped by the interplay of ordinary matter, dark matter, and dark energy. Observations of the CMB, such as those from the Planck satellite, confirm that dark matter is a significant component of the universe. Large-scale structure. The distribution of galaxies and clusters in the cosmic web matches simulations that include dark matter. Without it, the observed structure could not have formed within the universe's 13.8 billion-year history. The nature of dark matter. While the existence of dark matter is well supported, its nature remains elusive. Several theories propose what dark matter might be. Weakly interacting massive particles, WIMPs. These hypothetical particles interact only through gravity and the weak nuclear force. WIMPs have been a leading candidate for decades, with experiments like LUX-ZEPLIN and Xenon-1T searching for their interactions with ordinary matter. Actions: extremely light particles predicted by extensions of the Standard Model. Actions could solve several outstanding problems in particle physics and serve as a dark matter candidate. Their detection is pursued through experiments like ADMEX, which search for their conversion into photons in magnetic fields. Sterile neutrinos. These particles are a proposed extension of the known neutrinos. They interact even more weakly than ordinary neutrinos and could account for the dark matter. MAOCHUs. Massive astrophysical compact halo objects, such as black holes, neutron stars, or rogue planets, were once considered as dark matter candidates. However, observations show they cannot account for the required mass. Self-interacting dark matter, SIB. This theory suggests that dark matter particles interact with each other, explaining certain observations in galaxy cores that WIMPs cannot. Dark matter's role in cosmic evolution. Dark matter is the scaffolding of the universe, shaping the formation and evolution of galaxies, clusters, and the cosmic web. Its gravitational pull allowed small density fluctuations in the early universe to grow into the large-scale structures we see today. Without dark matter, ordinary matter would not have clumped together to form stars, galaxies, and planets within the universe's lifetime. In galaxy clusters, dark matter dominates the total mass, binding galaxies together and influencing their motions. It also prevents the hot gas in clusters from escaping, allowing for the formation of stars over billions of years. The search for dark matter. Scientists use a variety of methods to detect and study dark matter. Direct detection. Experiments like LUX-ZEPLIN and PANDAX aim to detect dark matter particles colliding with atomic nuclei in ultra-sensitive detectors. These experiments are placed deep underground to shield them from cosmic rays and background radiation. Indirect detection. Telescopes search for signals of dark matter annihilation or decay, such as gamma rays, neutrinos, or cosmic rays. The Fermi Gamma Ray Space Telescope, for example, observes regions like the galactic center, where dark matter density is thought to be high. Collider experiments, particle accelerators, such as the Large Hadron Collider, LHC, search for evidence of dark matter production in high-energy collisions. If dark matter particles exist, they might be created and detected indirectly through missing energy in particle interactions. Astrophysical observations, studies of galaxy rotation curves, gravitational lensing, and the CMB provide indirect evidence of dark matter and help refine theoretical models. Simulations. Advanced cosmological simulations, such as the Illustris and Millennium projects, model the behavior of dark matter in the universe, comparing predictions with observations. Challenges and controversies. Despite decades of effort, dark matter has not been directly detected, leading to alternative theories. Modified gravity, MUND. Some physicists propose that dark matter effects could instead be explained by modifying the laws of gravity at large scales. While MUND can explain certain observations, it struggles to account for others, such as the CMB. Primordial black holes. Recent studies suggest that dark matter might consist of primordial black holes formed shortly after the Big Bang. This idea has gained traction with the detection of gravitational waves from black hole mergers, but it remains speculative. Emergent gravity. Theoretical physicist Eric Verlinde has proposed that gravity itself may emerge from the entropy of the universe, eliminating the need for dark matter. This idea is still in its infancy and requires further development. The future of dark matter research. The quest to understand dark matter is entering a new phase with advances in technology and theory. Upcoming experiments, such as the European Space Agency's Euclid mission and the Vera-C. Rubin Observatory, will map the distribution of dark matter with unprecedented precision. Meanwhile, particle physics experiments continue to push the boundaries of detection, exploring new parameter spaces. The search for dark matter is not just about solving a cosmic mystery. It is a journey to understand the universe's most fundamental components. By uncovering the nature of dark matter, scientists hope to reveal deeper connections between gravity, quantum mechanics, and the origins of the cosmos. Dark matter, the invisible architect.
Dark matter remains one of the greatest enigmas in science. Its unseen presence shapes the universe, influencing the formation of galaxies, clusters, and the cosmic web. Though invisible, its effects are written across the cosmos, offering clues to its nature and role.
As scientists delve deeper into the mysteries of dark matter, they are not only seeking to complete the picture of the universe's composition, but also to uncover new physics that could transform our understanding of reality itself. Dark matter reminds us that even in the absence of light, the universe's most profound secrets continue to beckon. Dark energy, the force driving the universe's accelerated expansion. Dark energy is perhaps the most perplexing phenomenon in modern cosmology, accounting for approximately 68% of the universe's total energy density. Unlike dark matter, which binds galaxies together with its gravitational pull, dark energy acts as a repulsive force, driving the accelerated expansion of the universe. Its discovery in the late 1990s fundamentally altered our understanding of the cosmos, raising profound questions about its nature, origin, and implications for the universe's ultimate fate. The discovery of dark energy. The existence of dark energy was first inferred through observations of Type Iowa supernovae exploding stars that serve as standard candles for measuring cosmic distances. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, found that distant supernovae appeared dimmer than expected. This indicated that the universe's expansion was not slowing down due to gravity, as previously thought, but accelerating.
This surprising result was soon corroborated by other lines of evidence, including measurements of the cosmic microwave background, CMB, and the large-scale distribution of galaxies. These findings required a new component in the universe's energy budget, dark energy.
The nature of dark energy. Despite its dominance in the universe, the nature of dark energy remains elusive. Several theories have been proposed to explain its properties. The cosmological constant, first introduced by Albert Einstein as a term in his equations of general relativity, the cosmological constant represents a constant energy density inherent to space itself. In this model, dark energy does not change over time and is consistent with observations of the universe's accelerated expansion. Quintessence. Unlike the cosmological constant, quintessence posits that dark energy is a dynamic field that evolves over time. This scalar field would vary in strength and density, potentially explaining subtle discrepancies in observational data. Modified gravity. Some theories suggest that the effects attributed to dark energy could instead arise from modifications to general relativity on cosmic scales. These models propose new laws of gravity that could account for the observed acceleration. Extra dimensions. Theories based on string theory or other frameworks propose that dark energy may be a manifestation of additional spatial dimensions beyond the familiar three. These dimensions could influence the expansion of the universe in unexpected ways. Vacuum energy. Quantum field theory suggests that even empty space is filled with vacuum energy from virtual particles. While this idea aligns with the concept of the cosmological constant, theoretical calculations of vacuum energy density differ dramatically from observations, highlighting a major unresolved problem. The effects of dark energy on the universe. Dark energy's influence extends across the cosmos, shaping its past, present, and future. Accelerated expansion. Dark energy counteracts gravity, causing the expansion of space to accelerate. This effect is most pronounced on large scales, where gravitational forces are weaker. Large-scale structure. By driving galaxies apart, dark energy affects the growth of cosmic structures. Over time, it suppresses the formation of new galaxies and clusters, creating a more isolated universe. The geometry of the universe. Observations of the CMB show that the universe is spatially flat, a result consistent with the influence of dark energy. This flatness requires a precise balance between dark energy, dark matter, and ordinary matter. Cosmic fate. Dark energy plays a crucial role in determining the universe's ultimate destiny. If its strength remains constant, the universe will continue expanding indefinitely in a scenario known as the Big Freeze. If its strength increases, it could lead to a big rip, tearing apart galaxies, stars, and even atoms. Observing and measuring dark energy. The study of dark energy relies on precise measurements of cosmic expansion and structure formation. Key observational techniques include Supernova surveys. Observing type Iowa supernovae at different redshifts provides a direct measure of the universe's expansion history. Projects like the Dark Energy Survey (DS) and the Vera C. Rubin Observatory aim to identify thousands of supernovae to refine these measurements. Baryon acoustic oscillations, BAOs, these are ripples in the distribution of galaxies caused by sound waves in the early universe. BAOs serve as standard rulers for measuring cosmic distances and the effects of dark energy. Gravitational lensing. The bending of light by massive objects reveals the distribution of matter and the influence of dark energy on structure formation. Weak gravitational lensing, in particular, provides insights into the growth of cosmic structures. Cosmic microwave background, CMB, detailed measurements of the CMB, such as those made by the Planck satellite, constrain the energy density and properties of dark energy. Galaxy clustering. By studying the distribution and clustering of galaxies, astronomers can infer the effects of dark energy on large-scale structure. Challenges in understanding dark energy. Despite extensive research, dark energy remains one of the most significant enigmas in science. Key challenges include theoretical framework. Developing a consistent theoretical framework that integrates dark energy with quantum mechanics and general relativity is an ongoing challenge. Vacuum energy discrepancy. The discrepancy between the observed and predicted vacuum energy density off by a factor of 101. 201, 0121, 120 is one of the greatest unsolved problems in physics. Evolution of dark energy. Determining whether dark energy is constant or dynamic requires precise observations over cosmic time. Distinguishing models. The subtle differences between competing models of dark energy, such as the cosmological constant and quintessence, are difficult to distinguish observationally. The future of dark energy research. Upcoming missions and technologies promise to shed new light on dark energy. Euclid mission. This European Space Agency mission will map the geometry of the universe with unprecedented precision, focusing on dark energy and dark matter. Nancy Grace Roman Space Telescope. NASA's next-generation telescope will study dark energy through wide-field imaging and supernova surveys. Next-generation cosmological simulations. Advanced simulations will model the effects of dark energy on cosmic structure, helping to interpret observational data. Quantum gravity theories. Efforts to unify quantum mechanics and general relativity may provide insights into the nature of dark energy. Dark energy. The universe's invisible architect. Dark energy is not just a mystery, it is a window into the fundamental nature of the cosmos. By driving the universe's expansion and shaping its structure, dark energy challenges our understanding of space, time, and gravity. Its study pushes the boundaries of physics, linking cosmology with quantum mechanics and the search for a unified theory. As scientists unravel the secrets of dark energy, they are not only probing the forces that govern the universe, but also redefining our place within it. Dark energy reminds us that even the unseen can shape the cosmos in profound and unexpected ways, offering a glimpse into the infinite complexity of the universe. The multiverse, exploring the possibility of infinite universes. The concept of the multiverse, the idea that our universe is just one of many, has fascinated scientists and philosophers alike. While it may seem like the realm of science fiction, the multiverse hypothesis arises naturally from several areas of modern physics and cosmology. If true, it could fundamentally reshape our understanding of reality, offering answers to some of the most profound questions about existence, fine-tuning, and the nature of space and time. Origins of the multiverse hypothesis. The idea of multiple universes has ancient roots in philosophical speculation, but its modern scientific foundation comes from theories in physics and cosmology. Several lines of inquiry suggest the possibility of a multiverse. Cosmic inflation. The rapid expansion of space during the inflationary epoch could create separate bubble universes. In this model, different regions of space-time stop inflating at different times, forming distinct universes with varying physical properties. This concept, known as eternal inflation, predicts an infinite number of bubble universes. Quantum mechanics. The many worlds interpretation of quantum mechanics posits that every quantum event spawns new branches of reality. In this framework, the multiverse consists of an infinite number of parallel universes, each representing a different outcome of quantum events. String theory. In string theory, the fundamental nature of reality is described by tiny, vibrating strings. The theory predicts a vast landscape of possible solutions, each corresponding to a universe with its own set of physical laws. This landscape could account for the apparent fine-tuning of our universe's constants. Brain cosmology. In some versions of string theory, our universe exists on a three-dimensional brain within a higher dimensional space. Other brains, potentially hosting their own universes, could exist parallel to ours, separated by dimensions we cannot perceive. Evidence and observational challenges. Direct evidence for the multiverse is difficult to obtain because, by definition, other universes are separate and may not interact with ours. However, indirect clues and theoretical motivations make the concept compelling. Cosmic microwave background, CMB, tiny anomalies or patterns in the CMB could suggest interactions between our universe and others. For instance, cold spots in the CMB might be remnants of collisions with other bubble universes. Fine-tuning of physical constants. The precise values of the fundamental constants, such as the strength of gravity and the charge of the electron, allow for the existence of life in the universe as we know it. The multiverse provides a potential explanation. If countless universes exist, each with different constants, we find ourselves in one of the few that supports life. Mathematical consistency. The multiverse arises naturally from theories like eternal inflation and string theory, lending it theoretical support even in the absence of direct evidence. Quantum interference. While the many worlds interpretation of quantum mechanics cannot be directly tested, its predictions align with observed phenomena like interference patterns in the double-slit experiment. Types of multiverses. Not all multiverse theories are the same. Different frameworks propose varying structures and relationships between universes. Level I multiverse. In this model, based on cosmic inflation, the universe is infinitely large and uniform. Regions beyond our observable horizon may differ due to random initial conditions, effectively forming separate universes. Level II multiverse. Eternal inflation predicts distinct bubble universes with different physical constants and properties. These universes are causally disconnected from each other. Level II multiverse. The many worlds interpretation of quantum mechanics suggests that all possible outcomes of quantum events are realized in separate branches of reality. Level IV multiverse, proposed by physicist Max Tegmark. This idea posits that all mathematically consistent structures exist as physical realities, encompassing every conceivable universe. Philosophical and scientific implications. The multiverse raises profound questions about the nature of reality and our place within it. Anthropic principle. The multiverse lends support to the anthropic principle, which states that we observe the universe to be fine-tuned for life because only such a universe allows observers to exist. In a multiverse, life-friendly universes are just a small subset of the whole. Redefining reality. If other universes exist, our understanding of everything must expand to include a potentially infinite set of realities. Falsifiability. Critics argue that the multiverse is unscientific because it may not be directly testable. Proponents counter that indirect evidence and theoretical consistency provide a solid foundation for the hypothesis. Ultimate origins. The multiverse does not necessarily solve the question of ultimate origins. Instead, it shifts the focus to the mechanism that generates the multiverse itself, raising deeper questions about the nature of existence. The future of multiverse research. While direct observation of other universes remains beyond current capabilities, advancements in technology and theory may provide new insights. Cosmic microwave background, CMB, studies. Detailed measurements of the CMB could reveal subtle imprints of interactions with other universes. Particle physics. Discoveries in high-energy physics, such as evidence for extra dimensions or new fundamental particles, could provide indirect support for multiverse theories. Quantum computing. Exploring the many worlds interpretation of quantum mechanics could deepen our understanding of branching realities. Gravitational wave astronomy. Collisions between bubble universes, if they occurred, might leave detectable signatures in the form of gravitational waves. the multiverse, infinite possibilities. The multiverse hypothesis invites us to imagine a cosmos far richer and more varied than we ever thought possible. It challenges our notions of uniqueness and encourages us to rethink the boundaries of science and philosophy. Whether or not the multiverse is real, the exploration of this idea pushes the limits of human understanding, inspiring us to ask bold questions about the nature of existence and the infinite possibilities that may lie beyond.